Can you all hear me? All right, cool.
Can you hear me as well? Yeah, fine.
Looks like the mute is broken. Yes. Oh, I should have done that sooner. Sure. Yes, I do realize that talk is slightly different than in the program, but there's no massive people rushing here, so.
Good afternoon, everyone. Let me introduce you John McGurney, who has been working on crypto in FreeBSD for quite some time, and recently at Netflix.
So, hello. My talk today is on optimizing TLS high bandwidth applications in FreeBSD. I've been doing, as Olivia mentioned, I've been doing crypto work on FreeBSD for a number of years. Originally, I started being interested in it on Jelly for making sure my disk performance. I have done this work in with Netflix. I worked with Randall Stewart and both Scott Long. I originally presented this paper of work that we did back in EuroBSDCon earlier this year, but we have additional new exciting results that I'll be presenting today. So, also, I am a consultant, though I was paid for some of this work by Netflix. Any of the opinions expressed by me are solely my own and not of Netflix. They didn't tell me to say that, but I feel like I have to, so. So the question is why is TLS necessary? I mean, I'm sure you've heard a lot about the press and other stuff. And the interesting thing is Netflix has been encrypting their videos since day one. They've already had DRM protecting it using like AACS and other technologies for an extremely long time. But the interesting thing is that the video metadata is not actually encrypted. This means that ISPs and other stuff are able to actually look at what movies you're watching even without your consent. They can just watch this, sell that information to other people. And I'm not sure if there's any other cases of this, but in maybe other countries, that would allow the country to be able to block certain videos on Netflix that they don't want you to watch, because they can say, oh, you're fetching part of this video, we'll just 404 it or whatever, or fail it. And so obviously you won't be able to watch whatever movie they fill that, and so things. But the attacks have been ongoing on privacy for quite a while. Part of the reason I actually got interested in crypto was a number of years ago, back in 2006, Mark Klein released information about a secret NSA room that was, well, believed to be done in an AT&T Interpoint exchange. And this is the building that it was in. The reason this is actually very interesting to me is the fact is that during this period of time, I would go to get lunch right across the street from this building probably at least once a week. So the mere fact that this spying was going on right where I worked and eat, is very disturbing. And so that actually started on my realization that that even though we have done wonderful things with providing encryption and other stuff through SSH and other stuff, we have not actually gone as far as we need to do in order to protecting that stuff. More recently, Snowden released his docs in 2013, which, though many years after the Mark Klein, actually really ignited and exposed just how pervasive the monitoring was going on, and luckily finally woke up the world, even though there were plenty of warning signs long before that. And it isn't actually just government spying that we need to worry about. The other thing is that there have been recent cases of content integrity. TLS will actually ensure that the website that you go to visit is the one that you intended to visit. There are cases like with Comcast. They provide Xfinity access points in the United States. And if you buy Comcast service, they provide you with a cable modem that provides your house with Wi-Fi. But the other thing is that if you choose not to opt out, it will also allow anybody who has another Comcast Xfinity login to access your internet. When you did that, there was for a while there, they would rewrite JavaScript on the sites that you browse and inject their own ads. So in a manner, they were actually stealing ad revenue from the websites, and as you know, it's already very hard to make money off the web. And then there are other cases like Verizon. The Verizon case is when you had your phone, they were, without your knowledge, they were actually adding a unique code to all the websites that you visited, and there was nothing you could do to control it, because your phone, if you did like a packet capture or looked at the request, the HTTP request, this code was not present. It was actually being added later in the thing. And there was actually cases of people who were tracking the various ad networks. They were actually using this cookie, this unique code, to actually recreate their cookie so that they could track you even after you cleared your cache and other stuff. So all of these mechanisms are actually help addressed by using TLS. To go a little bit back to what I talked about with Jelly encryption and my history with FreeBSD, I started wanting to protect my own data and encrypt that. So Netflix uses they a number of years ago announced their Open Connect appliance, and some of these appliances are actually provided to ISPs in order to do caching at the late level in the stuff. Their appliances are based on 64-bit Xeon CPUs. They're running a version of FreeBSD Stable and Nginx. They are often very high bandwidth machines in the 10 to 40 gigabit range, and even now I know that they're looking beyond 40 gigabit because hardware is continuing to get faster and the demand for storage is demand for bandwidth is continuing. Storage ranges from like 10 terabytes to, in some cases, as large as 120 terabytes. In most cases, these boxes have a large number of long-lived TCP connections. They're often 10 to 40K connections, high bandwidth, obviously, ranging from a few megabits per second to, I believe, some of the Ultra HD movie streams are at 25 megabits. So they're quite a bit of data. So the classical web server was a very simple process. We're talking about how daemons have been written using BSD sockets for an extremely long time. You would just have a process, a request would come in off the network, the worker thread who was processing the web request would do a read sys call to the kernel. The kernel would do either fetch the data from the buffer cache or go to the disk and spend a while reading it. Then it would finally read it into userland memory where you requested it, and then it would write it back out. Part of the problem is that this I/O delay could actually take a while and other stuff. There were mechanisms that you could help work around it with select, but disk I/O, you couldn't do that. And so there are various other ways to help one. Back in the late 90s, there was a FTP server called ftp.cdrom.com that was for a number of years the busiest web server on the internet. It was probably one of the first web servers that maxed out 100 megabit back in the day, and so this was a lot of bandwidth back then. Part of the problem was that in the traditional classic web server, a lot of time was spent reading and copying memory around, because in this case, you actually had to do a copy from the kernel into userland, and then another copy into the network buffer IOs. So David Greenman created a system call called sendfile. And the advantage of this system call was that it allowed the web server not to have to read the data into userland. We could now entirely bypass the userland, and so it would basically say, here's a file descriptor for the I/O. I would like you to write a megabyte of the file data out the socket, and the kernel would go around, find the data, whether if it's in the buffer cache, it'd be in the buffer cache. If it needs to get it from disk, it would read it from disk. It would then it would then create the MBUFs to send out, point them directly to the buffer cache data, and then hand them to the network card for sending. And this obviously meant that you didn't have to do a lot of copies, and this allowed lower power machine to perform much better. But then when you enter TLS, so part of the problem with TLS obviously is that you need to encrypt it. I'll go a little bit more into TLS a little bit later in this presentation, but for now, part of the problem is that every connection in a TLS will have a different encryption key. So this means that no longer are you able to simply take the data, maybe encrypt it once, and then send it out. You now actually have to do the whole different encryption, and also on top of it, there are many different cipher suites supported. So there may be 5 or 6 different ones. So even if you had the same key, you'd then have to have the same stuff. So in a classic TLS web server, you have basically forced yourself to go back to the old way of doing things, where you now read the data into the userland, but now instead of just writing it out to the network, you now actually have to do all the encryption in userland. So The initial measurements that were done for the paper and other stuff was that send file improved performance by about 3 times what it was originally. And so that made a very, being able to do 3 times as much work with the same CPU is very helpful. One of the other issues with the original send file was that send file was a synchronous operation. If the data was in the buffer cache, it would be packaged up, get sent, and everything would be done and returned fine. But the problem is that there's a number of different papers done by Squid who did some of this other work, having your thread waiting for the send file to complete means that your thread is not actually doing other work in the other work. I'll digress a little bit about it, but there's many different ways of writing a web server. There's like the standard old traditional Apache model, which is where you fork an exec and you actually have a per process running for each of that. Or there's also web servers that are event-based, where you have a single thread and it will actually say, okay, process what I can on each of the connections as needed. This means that this allows you to have a lot less threads and a lot less context switch, but in the case of send file, you would not actually be able to, you would have serious performance hiccups because with send file, your single thread of execution would be delayed for disk I/O. And so, at least for Squid, they were able to address this by having, when they would tell send file not to immediately return if the disk wasn't in the cache, and then spend this off into another thing. There's also the async send file allowed them to get an additional 33% performance. Problem was adding TLS performance dropped performance quite significantly. And then obviously on traditional, non-send file servers, there was an additional drop. So the idea came about to what if we, because as I showed earlier, doing the SSL, what if we were able to move the SSL communications from userland into the kernel? And so the idea was to basically move it such that when you could continue to use send file in your application, but then there would be a little bit of code that would interpose itself between the send file system call and the network that would do the bulk encryption for you. This would save the userland kernel copies that was going on and the like. The question, though, was how do you architect your code and other stuff? So part of the problem is that before you can actually move any data over a connection, over a TLS connection, you actually have to do a set of messages to establish your key and other stuff. And this is the standard TLS handshake. First of all, the client connects and tells the server, hello, I'm here. The server responds to it, and then optionally, but in pretty much all the web servers, will include the certificate and the server part of the key exchange. This is not always included, but with modern forward secrecy cipher suites, this will always be included. Whether the server requests that you authenticate yourself with the certificate, which is actually very rarely used, and then the server sends its hello done. Then the client will respond with appropriately, and it will do its other half of like a Diffie-Hellman key exchange in order to establish the agreed key. It will send the change cipher suite saying I'm done, and the server, when it will also send the change cipher suite. So right now with TLS, all of the data up to change cipher suite is entirely encrypted, and then as soon as the change cipher suite message is received, all future messages will be encrypted using the key that was recently negotiated. And so that means that the finished message of the finished handshake will be encrypted, and also adds as a little bit of ensuring that the key that you both agreed on is actually the correct key. If you don't get the finished message, then something went seriously wrong with the handshake. So the TLS, to integrate TLS into the kernel, there were a number of some choices were made. One of the things that, in the case of Netflix, they are mostly interested in serving video data. So being able to just do the encryption in the kernel and not actually do decryption made things a lot simpler. All the key certificates, key exchange, and decryption still happens in userland. So, and the other advantage is that all the other unsupported ciphers will continue to work, and they'll only actually move the supported ciphers into the kernel, because it turns out that there are a few people who are still using older RC4. The other interesting thing about Netflix is that they actually have a limited, they have control over the clients. And so they're able to, they're currently in the progress, I'm not sure how far along they are, of only using ASGCM for all of that. And the big thing is that ASGCM is a much more efficient cipher on the server side and has lots of benefits to that, and they can limit that to others. So in order to be able to have the TLS convey the key to the kernel such that the kernel is able to do the encryption, 2 additional socket options were added, which cipher supported and cipher keys. So the cipher supported is just literally querying the kernel to ask what cipher suites you supported. And that is because the cipher suites that are available in the kernel may not actually be all the ones that you want to negotiate. There may be other ones that are, you don't have the proper kernel module loaded and other stuff. And so if you still want to be able to support it, you have to be able to do it in userland. And then the cipher keys for loading the keys that will be used in the thing. So this is the results that we presented at EuroBSDCon. These were very early preliminary results. As you can see, with no TLS on this OCA appliance, we were able to get almost 20 gigabytes per second reasonable. But as soon as we turned on OpenSSL, our performance dropped significantly to about 8.5 gigabytes per second. And with TLS with sendfile, at least the initial implementation was only 9 gigabits per second. And we were, as with all pieces of software, when you first write them, you have to get it correct first, and then you can figure out what went wrong in optimization. So there was a lot of work going on. At the end of the EuroBSDCon presentation, there were a number of different methods that were posited to improve performance. One of the interesting things is that some of the ciphers that we were seeing was AES-CBC in addition to ASGCM. AES-CBC is a very linear cipher. It means that when you process one block, you have to process the block fully before you can actually go on and process the next block. With the AES-NI instructions on the Intel architecture, the AES round instructions have a latency, depending upon what machine, of like around 4 to 7 clock cycles. It turns out ASGCM, which I mentioned earlier, that process, you can actually handle each AES block in parallel, and so you can actually use the pipelining features to get significant better performance. So one of the things that that we investigated a little bit of was the ability to be able to pipeline multiple streams of AES-CBC at the same time. So that way, instead of the inherently serialized version of CBC, you would actually like do 4 streams of CBC from 4 different encryption at the same time in order to hide all of those latencies and other stuff. The other issue is that when you're using AES CBC, you would also most likely be using SHA-1 HMAC or SHA-2 56 HMAC, which again is also a very serial process and cannot, the only good way to pipeline it is to use multiple streams. So there are some advantages and disadvantages to using real-world production in benchmarking in production. The nice thing is that you're testing what you get. If you don't have that problem of, well, I benchmarked it all and then I deployed it to production and I got 1/3 of the performance. What went wrong? But at the same time, when benchmarking in production also has issues in that you don't always able to control the load like you would. I know that Randall, a number of times, it was actually hard to get enough clients hitting an appliance to actually collect data. In production, if nobody's watching movies at that time of day, well, you can't collect the data. You're not going to be running the server hard enough. And you was like, oh, well, I can push 5 gigabit, but I'm only using 10% CPU. What the maximum load is? So, there's advantages and disadvantages to that. So it's definitely very valuable, but, you have to understand the limitations and the restrictions of it. So a number of improvements were made in order this. The RevD appliance is a spinning Rust disk-based appliance. Each of these graphs are about an hour of load. The OpenSSL, this is the traditional. One of the things that was done differently from EuroBSDCon till now was that at EuroBSDCon, all of the crypto was done through the Open Crypto framework on FreeBSD. Randall did some experimentation and he managed to import various cipher suites of both Boring SSL and OpenSSL into the kernel. Part of the reason this was able to be done is that he had set up a task queue to handle all of that, and so the whole async nature of the Open OCF framework was unneeded for his applications for this, because when you have control of the hardware with ASNI, being able to push the high bandwidth, you have all of that control. So the OpenSSL performed at about 6 to 12 gigabits per second. The Open Crypto framework, with some of my modifications in order to do segmented buffers and other stuff, was at about 16 to 17. And Boring SSL, they have different different assembly instructions than OpenSSL was able to hit 17 to 18 gigabits per second. The interesting thing about the OpenSSL is part of the problem is that when a new connection comes in, there's a large amount of CPU time spent doing the key exchange, key establishment that ends up thing. And so you can actually have the problem where you have this temporary connection coming in, and it consumes a lot of CPU, and so you can actually see where it backs off. So the other architecture about Netflix is that they do not actually want their machines to run full bore, because if they're running full bore, then they may not actually be able to serve the video data that you want. And so they actually have a mechanism to control how much, how many streams a server is serving out based upon the CPU load. And so they help ensure that, but that also causes problems with being able to measure the benchmarks, because you're no longer able to just send a consistent workload to the server. They also have a flash version of their appliance where it's all basically SSDs. I forget the exact technology underneath it. And the interesting so in these cases, each of these graphs are around from about 13 hours to 18, 19 hours of workload. And so as you can see with the OpenSSL version of this workload, there was an interesting interaction between incoming connections and the high CPU. And so, as long as it wasn't performing very well, it'd be like, oh, the load controller would say, dump a ton of connections at it, but then the CPU would spike, and then the thing would, and then the monitoring would say, oh, you're overloaded, I'm not going to send you any more connections, but then the bandwidth would drop off and rinse, repeat, and you have very interesting thing. So, as you can see, the performance also. I was just talking with Scott Long just a little bit ago, and a very impressive thing is that they on newer. It also turns out that different processors of the Xeon line perform dramatically different, and Intel has been improving the performance. And so on one of their latest flash cache, which is using the V3 Xeons, they are able to actually get a full 40 gigabits per second on an appliance. And if they added a second NIC, they could go a little bit further all out and stuff. So, future work, we're, support decryption, and so, I actually forgot to mention this earlier. One of the things that is done in the TLS protocol is that each segment of data is actually framed with into packets of data. The TLS protocol, the largest frame size is the largest amount of data you can include in a frame is 16 kilobytes, and so you need to actually encrypt the data and then wrap it around with the frame before you send it down the buffer. And so that's actually part of the other complicated bit of work. So in the case of when userland would actually still write fully framed data out the socket, and then the kernel would actually do the encryption and then send it. And when we receive data, we'd actually receive the fully framed data for decryption. So obviously, there's interesting to investigate the possibility of integrating this into mainline FreeBSD. There are definitely some huge performance benefits that we can get by doing it. One of the things that I really find interesting about being able to integrate TLS into the kernel is that you can actually end up with a daemon process, like an S-tunnel type process, where you do all the key negotiation in a high-level process, and you then load all the keys into the kernel for that socket, and then you take that file descriptor, and you basically say, no more key changes, and then you hand it down to a child process. And then the child process can do all the reads and writes as if it was a normal socket, but it will actually be fully TLS encrypted. And then there's no key material for that child process. So if the child process was compromised for anything, there would be no private keys in the child process. You have a question?
Would it be even faster and more secure to port the OpenBSD socket splicing API?
I have not actually looked at the OpenBSD socket splicing API, but doesn't that actually still involve the code going into another userland process, or does it actually?
You can splice to TCP or UDP. I'm not certain about UDP, but at least
Yeah.
TCP sockets go up to a certain number of bytes, and the kernel does the zero copy forward.
Well, so the problem with that is that even though you would splice it, you would still have. I'm not sure exactly. I think the splicing wouldn't actually do the encryption, which you need, right?
No, the splicing doesn't encrypt, but now the
Well, yeah. So yes, then you could use something like that to do. And so the question, I forgot to repeat the question, which was, could we use the OpenBSD splice system call to do that? So, but yeah, so coming back, being able to have a file descriptor that you treat as a normal file descriptor that you read and write, but have full encryption, decryption, be able to not have the userland process have any keying material and other stuff means that now you can be able to write much more secure software and be able to reduce your attack surface. So, well, that's pretty much all of my presentation. Does anybody have any questions? Yes?
So Mark, you mentioned that you were looking at using real traffic for...
Yeah.
I know at least at VeriSign, when we look at, whenever I design stuff for VeriSign's Edge, it almost never includes null traffic.
Yeah.
It's always designed for attack loads.
Mm-hmm.
So what are you doing in that case for DDoS attacks that target TLS? You know, something like garbage in the handshake or renegotiation after the handshake. Did you do anything specifically around those?
Scott, do you want to answer that question? So the question, let me repeat the question. And so the question was, at VeriSign, they actually designed their production loads to be able to handle DDoS and other stuff. What does Netflix do in order to do like garbage and handshake and other TLS attacks? Scott?
That's a very good question, and prevention mitigation is really hard to do. For us, our model is that we don't do a whole lot of protection mitigation on the machines themselves, whether it's TLS or it's just regular DDoS type of stuff. We rely on the fact that machines are pretty much disposable. If the machine gets taken down, there's a bunch of other machines that can pick up that traffic. And if there's enough attack going on that a whole cluster, a whole data center is under attack, then we rely on network mitigation above that in order to practice.
So just as a repeat that basically the machines are disposable. If it goes out, there's another machine that can handle it and address it at a higher level than that. So, oh yeah, and actually it turns out that there's the TLS handshake itself is, as you know, is in a very expensive process, and it's very there's actually, I believe, an ongoing attack that it's very cheap to basically connect and then make the server do a bunch of work, and then you can just disconnect and repeat the same thing. And so I do know that there are some people who are working trying to figure out how to, so to say, do like a proof of work concept or something in the TLS in order to help mitigate that. So, you know, like basically, you know, having the server send a nonce or whatever, and then having the client actually do a certain amount of work before, you know, that is easily proved to the server that they're a real client as opposed to just spinning their wheels. So that is an interesting ongoing attack. It's a big problem because all the key exchanges are not cheap operations and stuff. So, all right, Colin. Yeah, Scott, if you want to. So the question was, could you use a variable bit rate to actually still unmask what movies are going through? I mean.
We don't do a whole lot of PGR stuff, do we? It wouldn't matter because clients shift up and down bit rates and do all kinds of other things on the same socket. And so fingerprinting that way is not terribly effective.
And so theoretically, you know, this is one of the standard, like, what side channels are out there, and there's lots of different side channels. I've thought about this on other protocols and other stuff, and it's a very difficult thing because, you know, they can figure out chunking, and they would, part of it is like, yes, if they actually collected enough information and basically managed to watch every single Netflix video on every single bit at every single bit rate and collected this database, then yes, they probably could. But I doubt an ISP is actually going to spend that time to collect that. Yes, there could be some third-party service that goes through and collects that information and starts selling it. But then, you're always going to have to collect more information, and you're only going to have, so to say, an approximate idea of what movie is being watched, because even though there's a lot of movies, you're not going to actually know exactly how much sizes and stuff. So.
But yeah, the big thing is that on the same socket, the client can be requesting different bit rates that are actually different files, and as a listener, you never know that difference going on.
Yeah. So yeah. All right. Any other questions? So, all right. Well, thank you for.
And like for the other,
Can you hear me?
No.
It's fine. Like for the other speakers, you get
wonderful piece of bread from Sweden.
Thank you very much.
So we have something like 20 minutes before the next talk.
just plug you in.
Try turning on.
Oh my gosh. Whoa.
Check it.
Testing 1, 2. Whoa. Oh, gosh. I'm sorry. Testing 1, 2.
Faster. Okay, have a seat, everyone. Faster. Okay, let's start for this second talk in the afternoon. Let me introduce you Michael Dexter, working from in IX System, speaking about FreeBSD and virtualization.
Thank you. And I wear many hats, depending on the time of day. I just bought a foundation hat, and I suggest you all get a lovely, nice, warm, ready for the Swedish weather hat. Got it? Good. Welcome, welcome. People are still trickling in, and I will begin gradually. This talk has been about between 4 and 25 years in the making. Thank you for your patience. So today I'm talking about options on FreeBSD for virtualization, but I'll touch on many subjects relating to all that. It's great to be back in Stockholm. I haven't been here for quite some time, and I was almost Swedish thanks to a refugee situation long ago after a big war. Let's dive in. Motivations. The Americans in the room may recall the big, giant computer shoppers, this massive book of everything available, every operating system out there. And it was inspiring to see so many different options as we've gradually whittled it down to very few. And if you were in academia, you probably, like myself, at the time in college, you probably bumped into all these different Unix systems and Usenet flame wars and other great things. And it was exciting, and I'm so glad that Paul Vixie touched on a great many topics that I'll touch on today. And what was special about January of 1991 in this field? Any recollection? Lawsuits, yes, correct. And what about alternatives to BSD?
Someone was playing with Linux for...
And he couldn't get it working to his liking. So months later, Mr. Torvalds from across the pond here came up with Linux. And I'm very, very appreciative that I started, perhaps like Paul earlier, in a pre-Linux environment. It was nice and simple. But with all those choices available and the amazingly high cost of hardware at the time, I wanted one keyboard, one machine, and I'd love to try those operating systems. I will not rule any of them out. They sound exciting, and having the Mac available was nice and pretty, but not very stable, and having a Unix system at school was quite educational. And all those nifty things in the previous slide were just things I wanted to try. But I could not afford a Next Station when they came along. I could not afford most of that hardware. There was no Craigslist yet. And they were the dark ages. So that was a bit much to ask at the time, I confess. And over time, as Paul touched on, we've had various forms of application and operating system containment. And as you've probably heard in the many talks from myself and Kristaps Johnson's while he was here in Stockholm and attending many EuroBSDCons, multiplicity is a term we often like because it's often the plurality of resources, and that high-level pluralization rather than specifically emulation or virtualization and fine differences outlined by Popek and Goldberg in '67 with the original hypervisor paper. So I've had a long journey. It's been at times inspiring, at times depressing, and through BSD-LV, Kristaps and I have contributed sysjl to OpenBSD, but Robert Watson blew that out of the water with his concerns about the safety of the systrace device, unfortunately. Thank you, Robert. I wish he was here to hear that, but he knows it. Later, the mult pluralized NetBSD kernel, and it turned out that running mult under NetBSD Zen, because you could run NetBSD on NetBSD quite easily, was very useful for development. And to hear that Kirk is using certain technologies for developing kernels is most rewarding. So in 2011, two folks introduced a nifty, promising project that I'll elaborate a lot on today, and I was the first outside user of that. And things accelerated this year with Zen arriving in the base system and through ports, and Docker, which I do agree that it has its place or perhaps doesn't, but people want that. So I'm not sure if anyone here attended my 2008 EuroBSDCon talk on very much the same summary, but there was some good news, but not a lot of great news. I mean, it took reaching to things like SimH and GXEMUL to say, hey, there's some permissively licensed emulators out there. Has anyone, run a DEC station in emulation? So a lot has changed, but first comes the context. Why BSD? And again, Paul, thank you for covering some of the key points, but it is, let's say, very open source, permissively licensed traditionally, and quite logical and digestible to most users and developers. It's been pushing key internet packets from day one, and Kirk's given some fabulous talks on that. And because it was government funded with a very clear goal in mind, it's been not a hobby, not a toy, not a research project per se, like Mr. Torvalds' project across the water there. As a extension of traditional Unix, it is genuine Unix. That represents some very, very, very long-term thinking. And in the big picture, as it applies to this talk today, it is a natural containment environment, in my opinion. We have things like fixed points of reference. You know exactly where the source will be all the time, unless you've done something local, but it belongs in a specific place. We have external third-party software ported in ports. We have things like the kernel configuration file, which is easily modified, and you can remove what you don't need. In FreeBSD, you can modify what's built. And it's all within a single environment, and you can safely disable things, safely remove things, and generally the system will continue to work. I once asked at a local meeting the then Ubuntu release manager, Alison Randall, who's a wonderful person, how do you check out and build Ubuntu? Because as I'm giving this talk, I just did the long one-liner to do a kernel and userland build and release with some nifty new software that's landed, and it was essentially one line, but, well, Ubuntu's not so simple. You have all the different package teams come together and bring their stuff together from upstream and blah, 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 and God help you come up with an ISO at some point. Sorry, I asked. And we have actually seen some very good progress in software packaging. Traditionally, package add on quite a few systems, package thanks to Baptiste, package source on NetBSD, which is getting a lot of attention in, say, the Illumos environment, SmartOS. It works great on the Mac, which is nice. And they've been very good about cross-compilation and multi-platform support. And in that natural environment, each BSD has had its strategy for slimming things down, be it NanoBSD, in FreeBSD, FlashRD on OpenBSD, NetBSD, everything, because it's been on just about every embedded platform out there. And has proven very useful to a great many people. As part of that legacy of containment, I believe the chroot syscall was invented to help package the entire system, but then, correct me if I'm wrong, I believe a young Bill Joy thought, well, what if we prevented processes from escaping that? And containment in this regard was largely born. That led to interesting things in Compat Linux, and that's parenthetical to it, but is proving quite useful together. Eventually FreeBSD.jo from Paul Henning Kemp, and naturally NetBSD was a very early Zen participant, first-class platform back in the day. SysJail had its brief moment of glory, and Colin has been working with EC2 for quite some time. I believe it was the 8.3 release that became quite usable on EC2. So we've had decades of great technology, elegantly simple licensing, great people, you all owe yourselves a round of applause, and humble marketing, which means that, well, it hasn't really reached the mainstream at times, and
Humble means like no marketing?
well, you're all here today, so there is some marketing. Someone's succeeding at something, but it's not quite as noisy as a great many things out there. So a result of just this, how did Paul put it, the attitude, the mindset, the whole BSD thing, are small but very effective companies like Alan with his CDN, it's just a handful of people. Tarsnap, it's one person or more, how many? 2. It's 2 people to offer a very useful service. Netgate, hardware with operating systems, I assume a small operation, but very meaningful software. PF Sense has been extremely popular in exposing the muggles to the things we do and saving money with it and securing their networks with it. And Henning Brouwer's ISP, the packet filter guy moves packets for a living. That's a very good thing. That is dog fooding as good as it gets. So as I touched on at the end there, work smarter, not harder. Just step back, think about the problem, and that gives us things like Mandoc, and I'm so grateful for Chris Stepps for coming up with that, where we can keep pushing graph around, or we ditch most of it, use the macros, and simply give the man page to the user. And of course, as Paul so kindly touched on, it's the ZFS silly. That's particularly in the FreeBSD environment. NetBSD, as I confirmed in Tokyo, is at ZFS version 13. It was imported, but not given the love it deserves. And we have exciting things similar in Go, like HammerFS, and I know a great many projects are excited about that, and I wish them the absolute very best. We need choices, we need stable options, and we're all benefiting from what comes out of that. So ZFS, for those who by some chance aren't familiar with it in this room, has institutionalized checksuming, it has low-cost snapshotting and cloning, and it is insanely flexible. It is a natural set of plumbing and foundation for all things virtualized and contained. I highly suggest you check out Michael Lucas's and Alan Jude's book that came out just a few months ago. It's fresh and up to date, and there is an advanced version on the way. So I do storage support in my day job, and I've been working with virtualization in its various forms for some time, and for what it's worth, I'll hit you with one buzzword: hyperconvergence. That's what they call virtualization atop storage. So let's fast forward to 2015. VMware is the market leader. There were some very well-timed tweets yesterday about how they get the hard part right, the virtualization, but the management part is not done right. And how do you get that wrong? But such is life. But funny, they are in court as we speak in Germany about GPL compliance. And thinking back to the day job, in researching storage vendors based on non-BSD operating systems, I must wonder how many are compliant in any way. So watch this space. So fortunately, open source is winning. Paul touched on the economies of scale, and if, say, Facebook with, let's just say 1 billion users, had to pay a $50 client access license fee per user to Oracle, and then $1,000 per CPU per server. That adds up really quickly, and for that money, they quickly realized you can have the best humans on the planet working on that software for your needs and get something completely tailored to what you need to do. So I think the overall business project community has grown in wonderful ways, and we're seeing donations back and forth and code contributions, some of which are very key to what I'll be talking about today. And it's huge progress, and nothing was stopping that over the years, but it's taken a long time to mature. So I will argue that proprietary software is losing, and niches are still well defended, but good luck with that. I have blackness. No. I have a delay because I'm still building World and back, so sorry about that. Never do that. Just don't. So they're losing their battle, and things like, a database like Postgres, it's really capable. And those who are willing to accept and improve upon any rough edges are benefiting wonderfully, and power to them. And along with that was hypervisors. They were unimaginable. We had Box, B-O-C-H-S. Like, woohoo, we got an emulator that kind of barely does its thing. So I'd argue virtualize or die. I couldn't run all those guest OSs way back in the day, but now I only want a guest OS that runs under some form of convenient hypervisor or emulator or thereabouts. I believe developers get this. Those who are building FreeBSD solutions are typically doing it on Beehive. The hypervisor I'll touch on later, and it took time. It took time. So virtualize or die. As the slide touched on, applications need to be virtualizable and containable, and operating systems need to be containable. The entire stack needs to be containable in some way, and fortunately we have lots of ways to do that now, and administrators and developers get that. So, stepping back here and now, we have, while it has some rough edges, we have the environment you want. We have very proven lightweight containment with jails. We have Zen, which does have perhaps more diverse guest OS support. We have Docker for what it's worth, and I'll touch on how it's uniquely done in this environment, and Beehive, and of course it's all on top of OpenZFS. And that is making for some very interesting progress. For the person who has not heard of jail in this room, it's a lightweight containment system that's been alive and well for 15 years. It's extremely well proven. And there are various projects out there that make it usable. There was a discussion this last 2 days at the FreeBSD Developer Summit about what should the next generation of jail look like. There are various rumblings about common configuration formats and the idea to move the jail.conf to something easily parsed. And EasyJail traditionally was a very popular jail management system, but it didn't have ZFS orientation, shall we say, and IOK just come along with a very low-level ZFS orientation. And for those who have heard of the FreeBSD VPS project that has nifty live migration, it's a very intrusive patch that would allow for jails to live migrate. And it needs a lot of love. And maybe that can be broken down into a bunch of separate tasks, but that is a fresh bit of information as of this week. So Beehive took a long time, but fortunately with that experience, getting the right people to talk to one another about getting Zen in the system was a very effortless, wonderful, delightful project with some very delightful people. And so here and now, FreeBSD has very modern Zen support. It is hardware assisted, that's indicated by the HVM, and if you come out of a familiar Zen environment, well, your existing virtual machines should work on FreeBSD. We have the benefit of OpenZFS, of course. And Zen has a remarkably strong community. Power to them. I'll touch on what's unique about that community. Roger, I guess, couldn't be here this event. He's near Barcelona. He's been upstreaming the latest Zen code, the 4.6 release that should be available this month. Apparently has live migration, which could be a killer app for certain people, for certain applications. And naturally, ARM is on the way. That's a very, very hot topic. And let's hope that lands sooner rather than later. The wiki is reasonably up to date at wiki.freebsd.org/zen. And in all useful business-oriented practicality, Amazon EC2 has been quite stable for FreeBSD uses for some time. And as I understand from Colin, the most recent 10.2 release has completely ready, off-the-shelf, officially built images. And thank you, Colin. I know that there are users out there, including himself with his business, that benefit from that. There you go. Yeah. So, really short on the on the heels of the Zen announcement was FreeBSD Docker. Someone had been working on it and got it working at BSDCon this year, and it coincided perfectly with the introduction of 64-bit Linux compatibility, on which it depends for most off-the-shelf Linux images. People want that. That's good that we can give it to them. Now, by default, Docker was never intended to be a secure containment environment. They deferred that to other external components. Fortunately, they've made that pluggable, and fortunately, that plugs nicely into jail. And there's the talk of disposable machines. They should start up quickly, be read-only, dump them when you're done. Well, we happen to have a file system that is proven and is really good at cloning and cookie-cuttering virtual machines, snapshotting them, cloning them, adding the persistence you might want if you want it, or disposing of the results. So Docker on FreeBSD is quite compelling if you want that. Consensus sounds like we generally don't want that, and I'll talk about why that is. So for those who aren't familiar with Docker, and I've had to learn some of this stuff, it's very much a sysadmin's view of the world rather than a developer's or DevOps or operator's view. If you have an upstream OS from Red Hat and you can't mess with it, and you have your cloud provider that you can't mess with the plumbing of, you have a very little bit of wiggle room to do something. So Docker focuses on pushing around stuff to get the binaries in a controllable environment within an uncontrollable larger environment. But we've had a very malleable, reliable, full environment that is very easily modified. So we don't typically have that problem. And my working analogy is the Latvian spelling bee. So the Latvian language is phonetic, and we don't have spelling bees. It's quite obvious how things sound and should sound. It's a bit like rattling off numbers, like, oh, 234, 234, great, Johnny, you nailed it. So we just don't have those issues. So leverage your environment. We have a very flexible environment. It's very well thought out. It is very unified. It has common kernel styles. It has common man page styles. It has common DocBook, Benedict is nodding, documentation styles. And so if you sit back and think, I wonder if this will work, it probably will. It's just pluggable. It's malleable. Ooh. Can get a drink while it's refreshing. Oh, come on. Oh, there we go. So in this new era, honorable mention to Cloud ABI. I believe there's a talk on it tomorrow about that. And that's a stripping down of the traditional environment, removal of syscalls, and achieving portability by cutting out the cruft. I believe it leverages Capsicum, which is an up-and-coming FreeBSD containment technology, and go for it. The environment is ready for such experimentation. And about those communities, Zen and Docker, I'm not convinced they want to be GNU Linux people. I like to think they are Unix people. I like to think that we have, even if they don't want to change a single thing in their workflow, we have an environment, and clearly with ZFS, we have a very good environment for what they want to do. So if you have an opportunity for outreach to these environments, go for it, please. We need new blood, we need new technologies, new funding, new fun people. So out of all that activity of people bonking heads and Dockerizing, interesting ideas are coming out of it, to their credit. We get things like unikernels, and I believe out of NetBSD rump kernels, user space kernels, which apparently are quite useful. They've had even poorer marketing than any of the technologies I've mentioned so far, so do find out about that. I'd love to see a talk on the current state of rump kernels. And in all of this, it comes down to effectively server-side embedded development. Instead of doing a small router like we saw with the ARM presentation, we're doing that to applications so that we can have lots of them. And use the same tools, use the same techniques. There's nothing too unique about all that. So, but in all that experimentation, shall we say, to put a really nice spin on it, the bureaucracy of aggregate parts is expanding to meet the needs of the expanding bureaucracy of aggregate parts, and you get 1,000 Linux distros, you get 3 main Docker formats, you get all sorts of stuff, and keeping track of it is hard. And I'd give great references, but I don't know where to start. OpenStack was mentioned. There's Asterisk Stack. There's Cloud Stack. There's Apache Stack. Anything, I'm trying to think of all those cute, Cumulus, and just about any word you can find out relating to clouds has a unique software environment tied to it that has unique dependencies, unique documentation that needs to be run, and if you've looked at, say, libvirt, there's an extensive page of needs to be documented, needs to be documented, needs to be documented, and I don't know what to make of that, and I'm relatively informed on all this. I still feel like I'm a beginner, but such is life. So I say wield Occam's razor very, very aggressively, chop things down, and when you work in a unified environment with, say, predefined areas of the system that can be disabled at boot time or compile time, it will generally work as a result rather than promptly fail painfully. And in all of that, enter Beehive. Beehive was very unique in that it was the result of an unconference. There have been very few, I'd argue, one true BSD unconferences, and that took place at Hacker Dojo in 2010. Hopefully there are a few people here who attended that fine event. And for the virtualization session, rather than breaking up into little groups, we broke all the rules and got in one giant group. And we ran through all the currently available options, notably Zen, and there were very early objections to that. And just the clear establishment that we have a big gap in the system. There was a follow-up session with a bunch of, shall we say, business leaders in a small room up above. And then out of the blue in 2011 came a presentation at BSDCon at the Developer Summit about the Beehive hypervisor. And in 2012 that was merged into Head. And you can imagine over that time span the various kernel operating system releases. So it, I believe, started in FreeBSD 7 and moved on to 8 and 9, and it was an adventure. But fortunately, things stabilized in 2014. On July 20th, it arrived in the FreeBSD 10 release. And in that same year, thank you, John Baldwin, we'll touch on that, it showed up with i386 support. AMD support was quite often requested. I believe there are people in this room who wanted such a thing. And most recently, UEFI support. So what is Beehive? Beehive is a portable, hardware-assisted emulation-free, permissively licensed, patent, unencumbered kernel module and utilities. It has been a pleasure. What's that? Read the slide. But it's been a pleasure to work with a piece of software with no lawyers to talk to. Not even about just the trademark, no patents to our knowledge to deal with, and fortunately, very little code, very complex code, very, very, very complex code, but very little code. So about that littleness, the kernel module that does the heavy lifting or interfaces with the hardware which does the heavy lifting is under 300 kilobytes in size. I wonder how big box, B-O-C-H-S, yes sir? That is the executable. That is the kernel module you load as built in the current system, and that was probably me a few months ago when I checked it. I doubt if it's fluctuated much. The beehive command itself fluctuates quite a bit, but it's still relatively tiny compared to everything else out there. And the reason for that is that it's relying on modern processor features that flat out didn't exist except perhaps maybe in Popek and Goldberg's day on their mainframe, but we've been lacking those in the PC environment that Bill, was it Jolitz, established and got us into where we are now. So that gets back to the old work smarter, not harder. Let the hardware do the hard work. So leverage all the things, starting with, I believe, Nehalem class Intel processors known as Core i3, i5, i7, and their equivalent Xeons. I wouldn't necessarily go with that older processor, but Sandy Bridge onward, things got quite stable. And if you look in your D message, you'll see pop count, POP-CNT, and I believe they've even expanded on what identifiers are there to let you know that your hardware will support it. But I can certainly attest that there are some very competent machines on Craigslist that for, a mere $200 will get you a very, very long way. And in leveraging all the things, Beehive ran very quickly into the shortcomings of all the things it pokes as it does its work and plugs into. So, for example, it was a surprise that FreeBSD was the one OS we found that did not default to a serial port if it was missing a video adapter. Most other, more perhaps router-oriented OSs handled that quite nicely. The VirtIO infrastructure that it relies on, which is generic virtualized storage and network devices, needed its own updating. And serial devices. We found bugs in this NMDM thing I had never heard of that I trust very few people have used, but by wanting to just get that serial data from point A to point B, it revealed some bugs. And I suddenly want all my 1990s serial switches because they're suddenly really useful once again, because in a cloud environment, with air quotes, that is how we interface with systems. And that gets into things like UEFI and ARM. ARM is on the horizon, but ARM has, say, its own unique bootloaders. They're generally under pretty good licenses, but they don't generally build with Clang LLVM. Grub does not build under Clang LLVM. Grub hasn't had a formal release for a very, very long time, which means using its implementation of ZFS means we try to jump into the stream and catch up fish and use it and hope it doesn't change by the time we want to cut a release or something. So that's been most interesting. A lot of the barriers to Beehive's release were completely unrelated, I'd argue, to Beehive itself. But such is life, and you do find other people's bugs. Beehive itself is very performant. It gives bare metal CPU performance. There is room for improvement on all things I/O, VirtIO, storage, you name it. I'm not a networking weenie, but you talk to networking folks, and they always want something more, something different. You give them a bridge device, they want 3 more. You give them anything, and they want to throw a VLAN through it. It's like, okay, fine, you do that. So Luigi, make it so. You may be familiar with Solaris, Crossbow, virtual networking. All those projects suddenly get a lot more interesting in this context. And Benjamin, this gentleman in bright red, has been pounding on Beehive in production. If you have any questions about a unique use of it, he's the man. I'm so glad you're here today. Beehive is portable. That starts with the license, not the technology. And Beehive is showing up on OS 10. It is showing up in commercial projects, which they have every right to do. Unfortunately, some of these vendors have been extremely beneficial to the open source version. And apparently there's a fantastic BayFab talk on what TidalScale is doing with it. I haven't had time to see it. I encourage you to go check it out. Beehive is proving useful. Apparently parts of the FreeBSD build cluster use it. Scale Engine depenguinated with it. They had one CentOS box and didn't want to have one out of 50, maybe now 100 or more machines. So Beehive, even prior to its formal release in 10, ran their encoding software very efficiently. They can saturate any network interface they have, so there's one happy camper. The Linux Acquisition Executor. One of the key motivations for Beehive was a large storage company that produced it. And when they made their various acquisitions over the years, they were often on foreign operating systems like GNU Linux. And one could spend 6 to 12 months porting everything to FreeBSD, or they could drop it in a hypervisor. And that's proving very useful to them. And I don't have many stats on Zinus, but they're in the SCO classic cache registers game. And virtualizing old systems on 32-bit environments is quite useful to them. And the Dr. Kirk McKusick revealed that he's doing kernel development with it, and I profoundly appreciate that. Beehive is very capable. It's been running FreeBSD from day one, GNU Linux from very early on because it's met the needs of its original creator. As the kind of cross-BSD person, I encourage very early adoption of OpenBSD as a VM and NetBSD. As you may know, OpenBSD has recently announced their own hypervisor. It is not Beehive, and it'll be interesting what the landscape looks like a few years from now. And as for capability, as of today, we have UEFI support, and it supports Illumos SmartOS. On FreeBSD, it does FreeBSD UEFI, which might be quite useful for debugging that. Ed Mastery in the room, I forget who was working with the foundation on that, but that could be very, very useful. It supports Linux UEFI. And yes, as of today, it officially supports Microsoft Windows. And I did not pull a one more thing. Ha. It supports Windows 7, 8, 8.1, 2008, 2012, all the new betas and recent release of 10 and the 2016 previews. I can't help you 2003 server users. I believe you're end of life from upstream, so I'm sorry. Go run Zen. And a few nuts and bolts about that. This is all fresh information as of late last night and early this morning. Yes, 3 a.m. that hit. So forgive me for not having complete documentation, but I have updated the wiki. The key thing is the SVN tag, and my slides are slow because I am building that release, so I can try it out on the second little machine I brought, and I'm happy to hook anyone else up here with that release. Peter Grian has documented the build instructions and has some binaries for the UEFI payload there. And it was a bit embarrassing at BSDCon when we did have Windows Server running, but none of us knew how to disable the firewall or allow a download or just grab untrusted software to test the speed. It was like, and this one local student ran down and gladly helped us, and we're very grateful for that because we just don't know. We have no clue. We've collectively so avoided Windows unless absolutely necessary, as we touched on earlier. But the reason I say that is that currently it is headless. By not emulating anything, we get fantastic performance, but we sacrifice a few things, so that installing Windows requires unattended, completely official Microsoft strategy, additional software, little configuration files that, hey, here's the password I want, here's the user, here's my networking config. And most frustratingly for testing it, here's my license key. And as of this weekend, tinkering with this, it is my new life goal to remove the phrase license key from the human vocabularies. So, I will not go through those steps, but over the next few days, I'm automating everything I can and will gladly step through that with you. And Illumos is working as of today, too. The documentation exists. It's just not yet super human friendly. I put up a bunch of cleanup and the key links that I just showed at the wiki link of wiki.freebsd.org/beehive. And it's coming. I appreciate all of your patience on those various components. And I'll touch on the hardware contributions, but just as a general rule, every given developer has a small, perhaps home office laboratory with limited hardware. And any amount of testing you can provide, be it on unique hardware or unique configurations, is profoundly appreciated because I guarantee you're doing something that they're not doing. So do jump in there and do jump in the wiki with your discoveries, your tricks, your pain points, and ask questions. Those questions are amazingly powerful in these environments. And so new developments, there has been a GSOC project for ARM64 support by Mihai. I haven't checked. Yes, sir. We haven't. A news flash. ARM. Only 32-bit. Okay. So, okay. I'll have to correct my slide, but someone pointed out that it is ARM 32-bit support for Beehive. And do you have any status information?
Not recently.
Okay. Anyone? And I'll touch on why ARM matters in my humble opinion. There's been a project for Pixie booting support. That's on its way, although UEFI will perform a certain amount of that in Microsoft environments. That's compelling. There are at least 2 NetMap VirtIO projects for faster networking. They are on the to-do list to be reviewed and experimented with and cleaned up. But if you are a network driver developer, your skills are welcomed. And as I touched on, looking to the future, we're all fighting with our ThinkPads and our different keyboards and broken IOMMU and all this stuff. But looking ahead, ARM is gaining momentum, and there are various laptops out there that are quite affordable, and increasingly there's very performant high-end hardware, which we touched on two talks back. And what gets interesting is that you can typically get Xeon E3 performance at half the wattage in certain environments. When you're not emulating 1980 and the 1980 PC, you have a lot less stuff in your processor and entire hardware stack, which translate quite nicely to a very simple software stack like Beehive. So that's a trend, but things like the Chromebook Snow, which is a Samsung $200 or so ARM-based laptop that theoretically could support Beehive and would be great for developers because they're very affordable. They throw various errors that just need attention. They have the boot BIOS that cannot be built under, say, Clang LLVM. They have one simple surprise. They have a GPT name type that's not supported by the FreeBSD G part, despite the fact that it's a text string that just needs to be put in the source tree. So all this kind of work shines the light and reveals the cobwebs and roaches and other things that are all under our noses. So do get out there, do test strange stuff. It's highly appreciated. So the ecosystem. As it reads, go away or I will replace you with a very small shell script. The one key complaint is that Beehive doesn't have all the cloud stuff we touched on earlier. Asterisk cloud or cloud asterisk, cloud stack, cloud this, cloud that. So I would argue that the BSD environment, notably in this case FreeBSD, doesn't need much abstracting. Paul, you touched on simply writing your own script to do things because it's well thought out from top to bottom. So again, work smarter, not harder. And continuing from there, There's a great amount of excitement about managing machines. Well, a virtual machine acts just like a genuine hardware-based machine, short of a few little things you might want to adjust, RAM allocations and storage. So if you're using Salt to manage your hardware-based machines, it'll work in a virtual machine. Just, I don't want to hear about it. Maybe there are some hooks to do the short list of Beehive-specific things, but it's just a normal machine. And in testing it early on, it proved so performant that I'd pound on the keyboard and I'd be certain that that's, I'd lose track of the virtual machine and the hardware machine, and I'd reboot it and take the entire host down because I couldn't tell them apart. So from your administrative DevOps workflow, it's just another machine. So if you jump into, say, a nice, clean, raw FreeBSD system, there is an official way to run Beehive. It is included as vmrun.sh. It is simplistic, but there's a great way to try it out. It will only support FreeBSD guests, but that raises the question, to what degree should this operating system include components to support other operating systems? So what the proper strategy is in the big picture, I'm welcome to suggestions, and the developers are. One very, very interesting discovery on my part in my software, which I'll touch on very briefly, is that download mirrors are a complete and utter disaster. The BSDs are quite good about having, say, /pub/freebsd/snapshot/architecture/ you name it. In supporting every Linux I could find, I swear I have directories and paths and ISO payloads that have zero indication of what OS they are, zero indication of what architecture they are. That's not cool. I will fault OpenBSD for having install 5.6 for every architecture. I need to know if it's MIPS or AMD64, i386, you name it. So that's one point. And then I remember back in the 90s, Linux had like /etc/grub.cfg or some easy place to find grub, the config file for the loader. Nowadays, everyone renames it, replaces it, has a different ending for it, puts a date stamp in it, and I can't keep track of all that. I can't keep track of how to install all these different Linux OSs, and that's just not my problem, not your problem, but somehow that needs some love. And fortunately, Glenn Barber's been very receptive to just lessons learned in all that good, bad, and ugly of mirrors. libvirt officially supports Beehive, but the libvirt man pages or web pages have lots of to be documented sections, which is a bit disappointing. OpenStack and OpenContrail are being worked on by SemiHalf in Poland. Maybe one of them are around and can give us some update there. Building. I could take a look if you're curious, and I might lose my slides, but it's almost done. So, come on, there we go. If you do a search on GitHub with Beehive, you'll find a few things. Alan Jude's work that needs some update, I hear. We're all guilty of that. We're busy. Stephen Wills showed off Pangolin at EuroBSDCon a week or two ago. And that is a REST API that launches virtual machines. He showed me a nifty web-based console that I can show a little later. Having root access console on the web is probably not something you want to do, but for development, that's very useful. There's IOHive out there based on loosely, perhaps, or even tightly on IOCage, and I've lost track of CBS, or CBSB. So I've been significantly rewriting my scripts that have been from day one. They're strictly to help break Beehive, to find its cobwebs, its edge cases, its rough edges, its problems. So in all of that, I've seen hundreds and hundreds of Beehive-related panics. And I'm curious from you as users, have you seen many panics? Show of hands? 1, 2, 3, 4. Okay, out of 20, 40 people, And Benjamin, who is pushing it to its limits, says, no, that is awesome. My work here is done, or it's just begun, I'm not sure. So as a reference implementation, I've automated retrieving those Linux ISOs, et cetera, just because I don't want to futz around and sit there, and I don't have time to research them, so there are various templates to go find that stuff and slam in the grub strings to get things booted. As of last week or so, I have a simple web interface that I can show. And in banging my head against this for like 20-something years, it was very, very simple to add Zen support, and jail support, and QEMU support, which gets interesting with the ARM pre-built images. And I hope to add SimH support, so you can have your like DeckStation or otherwise. And VirtualBox shouldn't be too hard, because believe it or not, a virtual machine is typically a block device that it boots from and a memory allocation that gets associated with it, and not much else. Maybe there's some fancy networking, and I see that I believe QEMU is now using VirtIO, perhaps. Great, that shouldn't be hard to include. Everything typically begins with just a command line execution. That hasn't changed in 40 plus years. So I've chosen an RC syntax because that hasn't changed in a very, very long time. Works for me. I don't need REST, but then I realized if you have a simple web interface that is using classic CGI, you get a REST interface for free. You just save off a working string. So very briefly, I'd like to take this opportunity to issue some huge thanks to Peter, Neil, and Leon of now Nahani Systems, who have pretty much done all the heavy lifting on Beehive. Yeah, I am genuinely grateful, and to see that technology with no strings attached, and some very quiet developers who would prefer me be up here talking about it rather than themselves, which, believe it or not, frees them up to either code on it or surf in one case. It's worked out. It's worked out very nicely. He's Australian, yes indeed. What can you do? So, as I touched on, Beehive itself touches on a great many things. So, Brian V. has done amazing work with VirtIO, which was necessary to get off the ground with all things Beehive. John Baldwin is an animal. He's wonderful. He makes amazing things just kind of out of the blue. I suspect he did i386 support over a weekend and just kind of dropped it in. Like, oh, here you go. And I believe some significant money was thrown at that problem with no results, so bless his heart. And Tico Nightingale has been very key to making UEFI work. And I believe it's QEMU that has a sense of platforms. I'll have to look that up. But the Intel boards that Intel's producing for, be it educational or embedded purposes, are using UEFI. And their implementation is 2-clause BSD licensed, which made a user space implementation doable. That's arrived today for public consumption and improvement. There's plenty of room for improvement, but the classic UEFI implementation that's on your laptop or otherwise apparently cannot be redistributed. Thanks, gang. Yes, sir.
UEFI is funny because, so when Pluribus ported Beehive to Solaris, which is back to begin with, they did, because they ported to Lumos, but they needed UEFI support or something. So they ported UEFI to that version of Beehive, and then the version we have is ported from Solaris Beehive back to the FreeBSD Beehive, and then there was licensing issues and blah, 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 blah. It was completely convoluted. It was horrifying.
Summarizing, from a very experienced user, the porting process was very convoluted, but those issues have been resolved. And in the long term, well, for today's purposes, but in the long term, I hope companies start not thinking so chauvinistically about their product, their environment, because using a Unix philosophy, if there's a nifty tool, you might run the risk of cutting a finger off, but let's give it a try. Maybe we'll come up with something new with it. So, continuing the huge thanks, thank you, Alan Jude. If I was user 0, he was user 1, who approached me very early on to test it, and used it commercially very, very early on. He was probably number 1 with the Depenguinator. Thank you, Benjamin, who's been providing insights here. And if you do have questions about Beehive in production, I welcome you to corner him, and he's indeed tested all the things in heavy load environments. And I heard on a bad day you're running 7,000 VMs on 1,000 hosts. What's on a good day?
It's always a bad day.
It's always a bad day. Okay, fair enough. So that is the largest Beehive deployment I'm aware of. If you have one, please let me know or one of the developers know, because believe it or not, they're the last people on the planet to hear about anything neat relating to Beehive. Xhive came out of the blue, just developed in secret, fine, okay. So continuing, Misha Peters, who's also here today, provided some very early hosting and mirroring for some builds I was making, because I was working in a non-head branch, and well, it's easy to test if you just build a memstick image and hand it over to people. FreeBSD gets that right. Making a release is really simple, so simple I can do it while giving a talk. We can check on the status of that in a minute. And so Nicebug was also very good about a mirror over in the States. Misha's in the Netherlands. And we have a new Beehive fan of note, Paul. I added that a few minutes ago, and that was inspiring and rewarding. I appreciate that. And these are very exciting times. NetBSD Zen has been plugging along quietly with apparently Windows support for a very long time, but they didn't think to spread that word. OpenBSD has announced its hypervisor. OS X has its Xhive. But I've touched on this, but I'll just flat out say it. BSD is participatory. That means you attending conferences and people applying to give talks at conferences and sharing information and going to dev summits, which sometimes have really formal walls around them, sometimes are completely just in a hallway. Just dive in. Don't be afraid to ask questions. Don't be afraid to ask what needs help or how things work. The people are very, very kind. Help is always wanted. Find the bugs. If you've got a cloud thing you love, please experiment with it in relationship to any of these tools I've mentioned. At EuroBSDCon was a good example because it's very productively business-oriented. I asked the group in the Birds of a Feather session, so what cloud stuff are you using? Show of hands. And should we copy its behavior? And they're like, oh yeah, well, which one is it? Oh, it's the one we hated at our last job. And I'm like, okay, I guess the familiarity is leverageable, but you hated it and it was a bitch to install, and okay, I want better answers. I can put people in touch with one another, but I'm not hearing any happiness out of the cloud camps. But do spread the word. Do recharge, as Alan puts it, at a BSDCon. And please donate. The projects have their foundations. They're just getting this hat, which is needed for this trip. That enters me to draw in a drawing for a cool piece of hardware, and benefits my warmth, benefits the project, benefits the foundation. There is BSD certification, which is quite also best kept secret. It's been growing, but I believe there's a test each day of this weekend conference. That's quite cool. Do stay current. BSD Now has been a breath of fresh air in that environment. Will Beckman behind BSD Talk has been quite busy and does what he can. He came back with EuroBSDCon with quite a few things. I did some interviews long ago. You're welcome to check those out. And the FreeBSD Journal has recently materialized. It's very professional in a sea of blogs and Twitter posts and snippets of perhaps inaccurate news, but it has some very, very competent people behind it. Do get involved, and I do want to thank the late, great Paul Schinkefeld, who has small bits of code in my software, who had an ancient trick like reducing the console height for funny projectors minutes before talks, and has just inspired countless people, helped countless people, organized countless events, and has made EuroBSDCon what it is today. So I don't know if everyone knew Paul, but Paul passed away, as the other Paul touched on, and he was just fantastic, and we need more Paul Schenkevelds. So I'll say thank you. I'm happy to give a quick demo of my current parlor trick, and I have indeed dog-fooded this entire demonstration out of the whole presentation. I'd like to thank Glenn Barber, who couldn't be here today, but I was skeptical, but the foundation bringing on a release engineer was a very, very good thing. The trains run on time. Snapshot showed up, I believe, today, but unfortunately just missed the patches I mentioned earlier. But that is necessary, and it's taken a very long time to find out the hybrid perfect space between a bunch of volunteers doing a project and a few companies doing their thing. And I will give a very brief demo of the VMRC web interface, which is a shell script spitting out HTML, because that's how the web works for the most part, and I just happen to use a shell script, and I get to control every aspect of how it operates. So back in the day, Windows NT was really good for testing hardware because it was finicky. And for testing virtualization, OpenBSD is proving very useful. It generally runs. So I do a little listing of everything in my single pane of ass. And sorry about that. And I do have a simple little set of things that call my RC script. And if you want a REST interface, well, there it is. It's the URL. And as I mentioned, Swills turned me on to a JavaScript console. Did that sucker start? I pushed a stop button. That's at the start, yes, thank you. Okay, hop over here. Oh, and well, suddenly we have OpenBSD in a web browser with very little effort, and up it comes. For those excited about Windows, you can get the SIC, System Administration Console, I believe they call it, in Windows. And you get to learn about all those unique sets of Unix-ish commands that let you check the networking status, check a few things, reboot the system, which is useful. And then you hit it with RDP to get the visual interface. And I must say, as someone pointed out at BSDCon, the phone-based RDP clients are pretty darn good. They're shockingly good. I've given this talk over RDP. It's something that just has, they ditched everything and started fresh, and wow, good things happen when you do that. So let's see, we have an OpenBSD system running on my, it's an i7, $200 off Craigslist, and boom, my build broke, and let's find out why. So in the break, we can find out what went wrong there, but anyhow. Any questions? Free RDP is working fine on FreeBSD right out of ports. Just aim it with a password and a username and password and IP address, and no problem.
Tight VNC is what the Honey guys use.
Okay, Tight VNC is also suggested. It does RDP?
Yeah, that's...
Really? I didn't know that. Okay. So go to a conference to find out that Tight VNC runs RDP. I had no idea. I'll have to try that. Other questions? Oh, come on. That wasn't that good. Yes, sir.
Has there been any work in this, how to back up like 100 virtual machines deduplicating external components while they are running?
While running, I defer to ZFS and snapshotting to get you that, nearly up to date. That's all very well established, and this just leverages it quite well. I do hope to see simple suspend and resume, perhaps hibernate, so that if you hibernate a guest, relocate it, and with the proper shims, bring it back up, it survives. Live migration, true live migration is a very complex CS problem. But if your application can't handle one of many guests going down briefly and handing over a common IP, you're probably doing it wrong. So I don't get too hung up on the whole notion of a perhaps parlor trick. But we should have that in Zen shortly, and we'll see. Yes, sir. Jordan.
So in terms of efficiency, how is Beehive doing with over-provisioning scenarios?
With what?
The over-provisioning scenarios where you're trying to run, say, 50 or 60 VMs on a specific host, and over-provisioning them with the assumption that they're not offering to use all of their memory.
Sure. So the question from Jordan Hubbard was, how does Beehive handle over-provisioning? And for those who dabbled with Beehive really early on, you probably remember that you hard allocated RAM to the guests, deducted it from the host, and had 100% CPU on every guest. Well, that's been thin provisioned since, Yahoo Meet BSD. And so a guest will only use what it needs in practicality. Baptiste brought up some very, very good points about how we have a very high allocation and have coin-operated scaling of that. And if the user wants 2 more gigs of RAM, how can that happen perhaps dynamically? And yeah, those are the right questions to ask. And I believe it was just a question of the syscontrols giving accurate information that the OS can use, and hopefully it won't panic. And I was about to say, Benjamin, you probably have a few insights in production.
Usually, depending on the modern, about 5 or 6 virtual cores per physical is usually a safe number, which is honestly, right, you're running 2 14-core E5s is a ton of virtual cores, so it's not too bad. OS-wise, hard and software-wise, Windows doesn't like above 16 cores at the moment. Hardware we have 24 cores. Memory-wise, it's pretty much just use memory to run out. I mean, like anything. There are situations where I have seen VMs panic if you start swapping off the memory, but that's the only one. So it works pretty quickly. But yeah, don't try to do like 10 to 1, 10 virtual per core data. Like 6 is a good safe number.
So it's a ratio of 6 virtuals per physical. Okay, and you'll see an official limit of 16 cores, but you can change that in the source and go as high as you want. Please try it, break it, get back to us.
Last question.
Please get to us for the wiki with those numbers. I don't have that Xeon hardware with the 3 cores and all that. I don't. So please do, let's have that conversation in the hallway. Yes, sir. Okay, the question is about VTD pass-through, which allows one to pass a PCI device from the hardware host to the virtual machine. That was buggy on a lot of early systems. Vendors simply didn't know how to do it and got the BIOS wrong, which is very disappointing, but recent higher-end hardware handles it very well. There are some horror stories of how certain controller cards would wipe out your Z-pool because it didn't handle it correctly, but you probably shouldn't use that hardware in the first place. Performance should be native. That's a plus. There is not support yet, although maybe today that's different, but for the VGA BIOS on the card is not yet available to a virtual machine. But yes, everyone wants to play their games. I'm well aware of it. You'll have your game someday, but Benjamin, yes?
So the only video hardware that's been tested is the NVIDIA Tesla DP card, and that's mostly been for Windows RDP offload, when it's the hardware accelerated RDP.
Ooh.
And that works okay. It's limited testing. It's very limited, right? You know it works. You know how it works, and it works. AMD has some bugs with PCI pass-through. If you're Intel, it generally works. Westmere on their hardware has been tested pretty good. Some of the i3s and i5s had issues, but anything that's an E3 or an E5 is generally fine.
So I will repeat one key point there, which was that one can have hardware-accelerated RDP, which I simply didn't know a few minutes ago, and that's exciting. And with all these resources, it's do you take one CPU core and use it for your jelly encryption, and one pinned on a guest, and one pinned on all these sorts of things. So there's lots of work to be done there, but very, very neat things are coming out of it. I will be here all day. I'll be at the dinner, and I'll be here all day tomorrow. So please corner me. I'd love to hear your success stories, your questions, your concerns, and thank you very much.
Thank you, Michael. And like for other speakers, the nice piece of Swedish bread.
Tack så mycket.
One more thing, we found a pair of keys in this room the previous session, so if anyone has lost their keys, then come talk to me.
they were fine. But when
seems to be working. Want to introduce yourself? Otherwise, I'll do it. Freeze. Borrow me that far. Should we start?
Hello everyone. The next talk is given by Masao Ubayashi, and he's going to talk about the config framework for the kernel build. Thank you.
Hello, thanks for coming. My name is Masao Ubayashi, coming from Japan, and I talk about kernel build of BSD. Which or BSD shares its root from ancient 20 years or 30 years or which I don't really know, older config framework. And all BSDs have changed config framework slightly differently in the last years. And now they have slightly different frameworks, and they all believe they are the best, and they are all still stuck. And it's a little difficult to decide the start of this project, but I had wanted to fix or rather understand what is really going on in kernel build for long times, for at least 10 years or more longer than that. But last year I attended the last year's EuroBSD conference, and when I going back to the conference, from the conference, I built a kernel in the flight, and I noticed that kernel objects are built in the order of alphabetical order. It's nice, and we are already get used to that, and it's nice that you can see how far kernel build is going, but I wondered how it worked, and I looked into Makefile, and I found that objects to link or build are alphabetically ordered by using makes colon large O, command or operation, and I was literally shocked by that, by the code itself, and for myself, I had not noticed that fact for 20 years, and my kernels I built had objects alphabetically ordered, and I was unconscious about that. And this project can be said to as our journey to find something that explains the feeling I got at that time. Anyway, so let's look at how kernels are built. And this time I deal with basically NetBSD, but actually all BSD's kernel builds are still similar, and the idea are already almost same. Okay. So basically kernels. Okay. Our kernels build is basically made of two phases. One is config 8 command, and then you run make. And config commands takes many input, and mainly there are kernel config files. Sorry. And when you want to build your kernel like generic, it includes some other kernel config files internally. And the point is that kernel config files are either definitions and selections. Definitions is like a recipe how kernel files are, how to say, next. Okay, definitions are options or like a menu which you can eat, and the selections are what to eat. And you can select something you want to include your kernel. And there is a template makefile whose root is actually I just made sure that it existed the first version of config in CSRG repository, so I don't know who designed it, but it works like this in all BSDs. And then config generates some mysterious C files and generate a single makefile. And you run make, and maybe you makefile includes another makefile, maybe not, but you get a single kernel file. Do you build kernel by yourself? Yes. Do you read generated files? Do you read generated C files or make files? Why not? Why not? Let's try. It's interesting. And when you once look into it, you cannot help changing something. I mistakenly decided to look into it, and I could not help changing things. So if you complain my development and my change, I want to say just look into it and complain after that. Anyway. Okay, so NetBSD has some a makefile code, makefile cron inc, which is common machine independent or make logic, which is included from a generated makefile. It has worked for us, but it also had many mysterious codes which people usually don't look into. I also looked into it and could not help cleaning up things. Basically, kernel build is not that special. You build .c files to .o, and finally you link correct all .o files into single kernel. It's pretty simple and common to user-land. But it was terribly complicated, and still it is. And I think I thought it was almost unmaintainable, and it was abandoned. This was abandoned area, and I think I wanted to fix that situation. Okay, so for some time, I spent a long time to read those generated files to understand them. And to summarize, my conclusion is that from that observation, I thought most complexity comes from makes explicit rules. When you run config generate a make file in which every .c to .o, those rules are manually written, which is called explicit rules. And there is BSD Maker has functionality called implicit rules, which you specify a pattern .c.o just once, and if you say you want a foo.o, make automatically generates .c2.o rule internally. But config does not use it, and you have thousands of lines of explicit rules in the generated makefile. And it overrides everything. Yes. And many conditions, .if syntax and .for something. I also checked compiled object files binaries, and you get this is NetBSD kernel, and you objects. And if you build to make sure build is correct, and for example, you build many kernels, all kernels for one architecture like EVV ARM, it has many kernels, and you have to build not only generic but hundreds of kernels, and they have hundreds of same objects made from a single .c file. And I compared those object files. And EVV ARM with 7 hard float, and BSD supports many kind of combination of ABIs. So this is one with has 41 kernels and about 1,000 object files and 180 megabytes, a lot of files. They are very similar, but slightly different files you get. So too many duplicate object files you get. So you may wonder I wonder if I can share those duplicate object files. And hopefully it's better to reuse those object files. Yes, and there are sys modules which is used for to build dynamically loadable kernel modules. Different in another different directory, you get almost same copy of duplicate object files, which looks like very wasteful. So, modules. NetBSD has functionality called modular, which used to be LKM, meaning dynamically loadable modules. And it has different infrastructure in different directory. And separate make files and config files, and so everything is duplicated from kernel build infrastructure. So in NetBSD, those modules can be also built into statically linked kernel, but in this case, objects are built in kernel build infrastructure, not one in this different build procedure. So a natural idea would be that reuse all objects. If you build once object, reuse it for kernels and dynamically loadable modules. And I call it relinkable kernel or modules. And actually, those objects.o files can be reused or relinked using LV-R, and this corrected object is still the same format as input.o files. And if you correct one, for example, or FFS or IPsec or other any other functionality, you can correct those objects into single bigger .o file, and if you use it for kernel or dynamically loadable objects, it can be almost called as a module, even if it is not really a dynamically loadable module. So confusing thing is that the word module is used for so many things, and in NetBSD, if I say module, people think it as dynamically loadable module. But for me, module is just a collection of functionality. Okay. So the idea is to provide those object files as a module and build it once by the project. So NetBSD project, for example, built those objects and distribute it as the official objects, and the people link those objects as either statically linked kernel or dynamically linked kernel. Theoretically, this is obviously possible, and I think many people have thought of the same idea, but no one has realized. I think so. So this idea, I think this idea is sane, and this is a good long-term goal, but this cannot be done soon, and I decided to achieve, to set a more short-time realistic goal. And so I tried to simplify kernel bits, and with that long-time goal in my mind, which is linkable kernel or modules. So I started this simplifying kernel bits last year. And yes. So kernel build infrastructure was designed long time ago, and basically its basic design has not changed a lot, basically same. And now time has passed, and we have some more better tools like Linker scripts. Not much, but it's useful, and I wanted to use right tools to, if possible, to simplify things. Okay. Well, I have philosophy, and if I try to solve a problem and existing problem, and if something odd is found, and I guess the cause of them, and in many cases those problems or hacks was made because at that time people thought his problem was special, especially in kernel. You tend to think that kernel is special, or you are special, or you are busy, or you have family, or you have many excuses, and especially around kernel, there are many excuses, historical excuses. So I was careful about them. So I started to clean up config. I will explain it this later. Okay, so let's. Here is no. here. This is NetBSD7 kernel build directory. And this is generated make files, which I like to read. And you see these objects. It's small. So it generates this. This is very readable. I started to clean up, and then now in the head looks like this. This is more readable. Do you agree? And this was just that, but to help to understand what is really going on. I started to clean up output file, which people usually don't care, but it was that. And I cleaned up a lot of things, especially in the current makefile, only files, what to build files is defined in makefile, in the generated makefile. Like this. Yes. But in the past, okay, here. This is a make rule. If you build arc4.o from arc.c, here is the rule command, and you have thousands of these for no reason. These are all same. If you have identical code in C, you want to refactor it, but people have used these stupid makefiles for a long time, and no one has dared to fix it, and I did it. That is one, but I cleaned up many other things. Yes. I made a change to stop ordering object files alphabetically. And York complained it. I don't really understand, but anyway. So linker. If you want to realize a linkable kernel, meaning you build the object once and reuse it, everything will be solved at link time, not compile time. So link will become more important than now. And actually, linker has many good functions, useful functions, which we don't really utilize yet. One is that linker script. Linker script is just a script to instruct a linker how to manipulate elf sections when linking. While linking, it's similar to awk script. It's instead of line-oriented, it's section-oriented script. Sorry. Okay, so to realize the linkable kernel, I have to utilize the linker more and more, and linker script has to be used, always used in kernel build, but it is not really used. It is only used for aligning page boundaries where architectures have to map those sections differently by using paging. So it is not used on some architectures that does not use paging. And linker script is not a standard. It's just a GNU specification. It's a little problematic, but other newer linkers are following GNU being used. So, and another useful feature is input command feature. You can specify input object files using this command instead of putting all of them in the command line. And NetBSD has a function called link set, which basically does create some section like XXX, and if you have link set underscore XX in other object files, linker collects those sections into one and merge them in the resulting object. And if you specify the start and the end of those sections, you can collect this data from code without using if-defs, which is really useful, or which will be mandatory for a linkable to reuse objects where you cannot use if-defs, because if-defs changes object files, obviously. So kernel build has many hacks, and one is data injection. For example, NetBSD sometimes want to inject memory disk file system or splash just image file into it, and a hack called copy SymTab. SymTab is symbol table. Section is usually put into a section .symtab section which is not part of the program, and which usually debuggers read it from executable file, not from executable image in memory. This is basically written from file. But if you want to use it from kernel, and if your bootloader does not support reading it, you cannot read it. So the BSD has a hack to copy those SymTab into dot data or dot RO data or some main section. And this is tricky because the size of symbol is determined when you finally link. You can know the size only after linking all objects. So to prepare a array to put copy setup, there is a chicken egg problem, and there is a hack to solve this. So there are many hacks, but basically if you put something in make files that can change the content of object files. For example, -d something which may result in a different object because which changes if which a conditional compilation. And if you change .xxs or something in the main makefile, you don't know which object files will change its content by the new define, and so you have to define all the dependency, all the .o have to be rebuilt if the main makefile timestamp is changed. This is ugly. So I have cleaned up almost everything, almost every questionable things in make files and generated files. In the last 2 months or so. Sorry. And I implemented option minus large m, which I call modular mode. This is basically build kernel using kind of modular objects, which internally create an intermediate object collection of objects. And then you can choose those collections of objects like FFS or LFS or net or inet or into the final kernel. This is not useful alone because this only generates just a kernel. But this can be a groundwork for future because this intermediate object files, connection with object files is almost the same as dynamically loadable object, which is now built under sys modules. And I also implemented suffix subzero mode, which basically a NetBSD or other BSD build all kernel object just under kernel build directory, like this is here kernel build directory, and yeah, all object files is viewed here. And currently, and if you use subdirectory mode, basically files are viewed under direct subdirectory matching. Matching subdirectory in source directory, kernel source directory. This is needed because you have to, this is needed to use suffix rules. And the suffix rules is basically to have to match prefix part, and make has no notion about path, or it does not know about file system, and you have to make strings matching prefix. Otherwise, a suffix rule does not work. And if I can use suffix rules, I don't have to generate 1,000 of explicit rules, and it significantly simplifies the whole build process. And along this project, I have got many ideas, and I'm writing those ideas into this file to the file, and or about config, not only about config, but also kernel builder in general. And some time ago, someone confirmed it overly strict and ridiculous, but it is not ridiculous. It is overly strict because kernel build has come since 20 years ago, 30 years, I don't know, a long time, slightly in wrong direction 20 years ago. So if you want to get back in the right track, you need a strong will, a strong rule. So it is intentionally being overly strict. So you should not complain. And I'm really confident about the direction I'm going, and I think I can fix almost all infrastructure problems. But the real challenge is to fix, of course, if-defs or if-defs in .c files, and you have to fix all of them one by one, and that is the real challenge, and energies has to be spent for that instead of ranting. Next. So basically, I want to change config to do almost nothing, and everything important will be done at the link level. So basically, config will do nothing except correcting, choosing files or objects. And it can be done, but next step is to make it to not generate a makefile. Um, okay. So along this project, I have got many ideas, and I know I have found that most of problems, especially make, is not specific to a kernel build. And I want to introduce some EBU ideas about make. And okay, this is, if you want to build one program from 3.c file, a.cb.c, and you one library, and if you write a make file following typical textbooks, you have to write .c, a.c to a.o, one rule, and another rule, another, and maybe 4 rules, 4 explicit rules, which is very unnecessarily complex. I want to use suffix rules more to simplify things. And if you define, or if someone defined rules, patterns, those big picture compilation can be split into smaller problems, which each of which is very simple, because make automatically generates rules internally. And yes, you give, if you want to make one program which is our goal, and you give initial condition, and make internally generates rules to build, and to build this whole dependency graph. And you don't need to worry about a generation of these rules. Yes, suffix rules is a very old idea, but still very useful and not really utilized now. So now our kernel build procedure is very complex, and one reason is if you want to build debug kernels, single kernels, kernel build make files overrides how to build .o files, which really complicates things. If you define different build rules by giving different suffix, you don't need to override anything, which significantly simplifies things. That's one idea. And another idea is separate how and what the currently kernel build make file is really looks like this. It has what to build and how, and in the same single make file, and pretty much a mess. And actually, what really need to give to make is what to build. Make have idea enough knowledge how to build. So in the kernel build, if you define a kernel config, and kernel config generates make files, partial make files which have only what, meaning .o or .o files to be included. And this also needs suffix rules. Another idea is to use suffix rules for not only one-to-one like compilation, but in input cases like typically it's a link. By doing this, for example, if you define .prog, this should be LDS. If you define LDS, which is a linker script to execute a program, this is one-to-one association, and this can be represented as a suffix rule. And if this linker script has input commands which include or object files, this can be represented as a suffix rules, and or link commands in BSD tree can be written using suffix rules, and you don't need explicit rules, which can be simplify BSD lib MK or BSD program MK. This can be doable, and my plan is to realize this for kernel first and do next target change libc build. And if people don't complain it, I will change everything else. Okay, I did most of changes in the last 2 months without doing any day job. Well, I did, but I was really into this development, and I made a lot of changes. Sorry. And I counted the number of versions of make file .inc, which was the main file I modified, and in the last 1 year the version came from 170 to 1.250 or like something like that, about 70. And okay, only one third of those commits broke build, which is good enough, I think. Yes, but I broke build a lot, but it's working now. Okay. So one problem of NetBSD is people are too good, and the people want to discuss everything. And if I like it and I don't like it. Most of problems I have found and I have faced are solved by myself without asking any other people. And I think most of problems cannot be solved by discussion. But I'm a little sorry about my attitude. And people complain, but people actually NetBSD development is not really active it looks like so, but actually people really care and still read all this, although they look hiding and inactive. So in NetBSD development, review is done lazily, which is good. And I trust all other developers, and the important changes are well reviewed, lazy. So, listen. Okay. So, conclusion. I have fixed almost all kernel, not all, but many kernel build infrastructure problems and made it back into the right track, I believe. And the kernel build is actually not that special, not that complex, and it's really simple now. And I have found many make usage. It can be possible to significantly simplify not only kernel build but user and build, especially user share MK in the BSD is really a mess. Someone has to step up to fix it. And I also want to utilize linker. And yes, that's all. Sorry for my English. One question is, do I have ideas how to fix if-defs? And there are many cases, and one, for example, one is if-defs in init domain in kernel. Kernel's main function has a hard-coded sequence of initialization of subsystems, which is really ugly, and if there are many if-defs, my idea is to rewrite it using constructors, basically a pointer to initialization functions. If you link some subsystem object files, it has a single entry pointer to constructor functions. Linker collects those pointers into one sequence, and what kernel needs to do is execute constructors one by one. But to do that, you have to order those entries in the right order. And you have to keep track of dependency of subsystems correctly. I have idea, but I have not done yet.
Do you have ideas how to maintain that difference without?
Question is, one purpose of if-def is to change install kernel, small kernel, and the production kernel. Well, especially it's used in OpenBSD to shrink the size of kernel, but I don't think it's not the case in NetBSD. I don't know, but maybe you can have two functions, maybe long one and smaller one, and the red linker to choose one either one at link time. I don't know. So basically, what you can do is ask linker to solve problems, not CC. That's one idea. So my changes so far is not beneficial for users, not yet, but maybe later. Thank you.
Of the organization committee, this Swedish special bread to try for you. Will you be tight on time or?
No, I can cut it down.
No problem to cut it down. I would suggest to just wait 2 or 3 more minutes. Sure. Okay, next up is Aaron Thomas, who is going to show us how to create our own hardware.
All right. Oh, sorry. All right. Never used one of these before. All right. Was that better? All right, thank you. It's a little awkward. All right. So I'm going to talk about RISC-V. So the title of my talk is RISC-V, Berkeley Hardware for Your Berkeley Software Distribution. My name is Aaron Thomas. How many of you heard of RISC-V? Okay, so there's a few people. How many of you were at the BSD CAM event, the FreeBSD Developers Summit at the University of Cambridge? Oh, that's good, no one. So we talked a little bit about RISC-V there. So they would know a fair amount of what I'm going to be talking about, but since none of you were there, you won't get any repeated material. So RISC-V, I'll talk a little bit about the rationale for RISC-V and open hardware in general. So this is from a white paper, an article from a microprocessor report that the RISC-V team at the University of California, Berkeley wrote. And everyone here is fairly familiar with Berkeley, the birthplace of BSD. So this is, the paper is called The Case for Open Instruction Sets, and so I'll just read the quote. It's probably hard to read on the screen, but so it says, given that the industry has been revolutionized by open standards and open source software, with networking protocols like TCP/IP and operating systems like Linux, or BSD in this case, why is one of the most important interfaces proprietary? And so the RISC-V team's answer is there's no good reason. The ISA is an important interface. There should be an open ISA standard that people can implement without having to pay royalties. And there should be open hardware that people can start building on top of. And so, I mean, I don't really have to sell open source to this community. This is EuroBSDCon after all, but open source has a lot of benefits for a number of different groups. So educators, researchers, hobbyists, hackers such as ourselves, and various companies and startups. So if you look at FreeBSD, for instance, there's been various talks about the L41 course at the University of Cambridge. So they're teaching a real production operating system, FreeBSD, in their graduate OS course, which is great. It's great to have your hands dirty in a real system. For researchers, there's been a lot of recent research that the University of Cambridge has done doing hardware software co-design on the Cherry processor. The University of Illinois Urbana-Champaign has done a fair amount of work with safe code and using FreeBSD for security work. And then all hobbyists and hackers are doing interesting work as well. There's been talks on how Netflix and WhatsApp have used FreeBSD for building their companies, and that would have been a lot harder were it not for open source software. And so what the RISC-V team would like to see is they'd like to bring all of these benefits to the same groups, bring the benefits of open source hardware to these different groups. So educators, researchers, hobbyists, hackers, and companies and startups. So I was at the RISC-V workshop. There's been 2 of them. I've been to the last 2. And so they had a mix of these different groups. So you had people who teach computer architecture courses, you had various researchers doing computer architecture research, you had just hobbyist hackers, people who were just building homebrew computers, and various sort of startups who were kind of interested in using RISC-V because it's an open hardware platform they kind of get going with. And I myself have kind of fallen in all of these different groups. So I actually, at the university, I designed a ISA that all final year students had to implement. And if RISC-V existed, I would have just used that, and my students might have been a little bit happier. But so it's good for education. If you can have an open ISA that people can implement, and open cores that they can start hacking with, it's good for computer architecture labs and things like that. For researchers, you've probably heard about the Cherry project. There's a lot of people doing hardware software co-design. I'm working on a project doing that. And having RISC-V as sort of an open platform is very useful for those doing research. And if you want to build your own homebrew computer, there was a guy who's trying to build like a completely homebrew computer using RISC-V, and that was pretty cool. And for various startups, you may not want to have to license, go through ARM and have to license the hardware and go through the negotiation, pay large sums of money. So it's good for a number of people. So here's the sort of overview of my talk. So my overall goal is to get you, first of all, I want to tell you what RISC-V is. So if someone asks you after this talk, like later at dinner or whatever, after you've had a few beers, what is RISC-V? I want you to say that it is an open instruction set. So at the very least, I want you to kind of know what RISC-V is, but hopefully I can kind of entice you to either hack on RISC-V software or possibly hardware if that's kind of your interest. So I'll talk a little bit about the RISC-V history, what kind of came before it, kind of like the intellectual heritage a little bit, and then I'll also talk about the ecosystem that exists. I'll also talk about the RISC-V architecture itself. It's a little late in the day, but I'm going to be showing a fair amount of assembly code because to kind of show the privileged parts of the architecture. And I'll talk a little bit about the FreeBSD RISC-V port that's starting to kind of come up in the last couple of months. So it's fairly early, but there's been good progress, and we'll be sort of pushing on that port in the future. So the RISC-V project has sort of a really ambitious goal. So this is from Chris Osanovich gave a talk at the RISC-V workshop, and he said the stated goal is to become the industry standard ISA for all computing devices. So that means from microcontrollers all the way to supercomputers. They want to kind of displace all the other ISAs. All the peripherals within your system on chip or your PC, they want that to run RISC-V under the hood as well. So really, really ambitious goal, not easy to achieve. And then David Patterson was in the Boston area recently, which is where I live, and he kind of joked that our modest goal is world domination. And so this is kind of what they're going after. They really believe in this open hardware deal, and they think there are a lot of people who are interested in it and potentially can make something out of it. So in a similar vein, I thought RISC-V is all about making really kind of ambitious goals, so I'll make another ambitious goal for RISC-V. And so my goal is to make BSD the standard OS for RISC-V. So in general, what happens with BSD, so device support will usually come to Windows and Linux first, not always, but in general, and then so the various BSDs will lag behind. And so it would be nice if for RISC-V it's a new platform, there is a Linux port, but it's kind of early, if BSD could kind of be the standard platform. And I could see that happening for certain segments at least. If you're doing research, BSD is fairly nice because it's a fairly integrated system. If you do, especially FreeBSD because of Clang LLVM, and I think NetBSD also is getting Clang LLVM as well. If you want to do sort of hardware, software research, like across the full stack, having that kind of like tightly integrated system, having Clang LLVM, and all of this stuff is really nice. So that's one of the reasons why Robert Watson and all who are working on the Cherry project were able to make such good progress using BSD. And so, yeah, this is my ambitious goal that I'm going to add to the RISC-V list of goals. So I'll give you a quick overview of RISC-V. It's an open instruction set architecture specification. So you don't need to license the ISA, you can build hardware, and you don't have to pay any royalties. So if you want to implement a processor, if you want to build an ARM processor, you have to come to a deal with them, and you have to pay them some royalties, and it can take a while. And if you're a startup or if you're a small company, it'll be sort of hard for them. It'll be hard for you to come to a reasonable negotiation. One point that I should make clear is that RISC-V is a specification and not a particular implementation. So my title is a little like, I wanted a catchy title, so it's Berkeley hardware or for your Berkeley software. RISC-V isn't actually just Berkeley hardware. It's a Berkeley hardware specification, and there are many implementations by various parties, and some of them are Berkeley BSD licensed and some of them aren't, so they're proprietary implementations as well. So the key point that the RISC-V people want everyone to know is that RISC-V is a specification. You can do what you want with it. You can make commercial cores, you can make open source cores, but it's just a common specification. So if you remember one thing from that talk, from my talk, that would be one good thing to remember. And so they're targeting all classes of machines. So microcontrollers, 2 supercomputers, and there are people working on different cores in each of these classes. And so the way they do that is they have a very simple base integer ISA. So it has kind of like your standard arithmetic, control flow, that kind of thing, loads and stores. And then they have various extensions that you can add. And the nice thing about the RISC-V ISA is it's designed to make it very easy to add new instructions. So if you're a researcher, you might want to add different instructions for various accelerators or things like that. And if you want to add different IP blocks or other kinds of accelerators, they make it fairly easy to do using this kind of base ISA plus extension methodology. So RISC-V is called RISC-V because it's the 5th RISC chip designed at Berkeley. So it's not RISC-V, it's actually pronounced RISC-V, so RISC-V is the Roman numeral 5. And it was originally designed to support computer architecture, research, and education. And so I'll talk a little bit more about the history in the next slide. There's several open source and commercial RISC-V implementations, and they're implemented in a number of different hardware description languages. So there's VHDL and Verilog, which if you've done hardware design before are fairly familiar. There's also some newer higher level hardware description languages. One's called Chisel from Berkeley, which is an open source one, and BlueSpec, which is a commercial one. And they kind of make it a little bit more productive to design hardware. And then recently the RISC-V Foundation was established, and so the goal there is they're going to be kind of the caretakers for the ISA, and they're going to kind of start building the community. So that's actually been a great development. So the history, RISC-V was started by Krista Sanovich and David Patterson at Berkeley. Anybody, do you guys know who David Patterson is? All right. So David Patterson is known for coining the term RISC, which I'll talk about what that is a little bit later. Does anyone know what else he came up with? So he also came up with RAID, redundant array of inexpensive disks. So he's kind of a big name in the architecture field. So there's a fair amount of credibility behind RISC-V because they've been kind of doing architecture for a very long time. And basically everyone reads David Patterson's architecture book in grad school and undergrad. So they've been doing a fair amount of architecture research, and they started searching for a common research ISA in 2010. So they started, x86 and ARM are kind of like the obvious choices. They've got plenty of market penetration, very popular. The problem there is that the ISAs are fairly complex. I mean, if you look at the Intel manuals and the ARM manuals, they're thousands of pages long, and there's also IP issues. They're not open ISAs. So they decided to develop their own ISA. That's the summer of 2010. And so it was originally supposed to be sort of a 6-month like summer project, and turned into this like 4 or 5 year quest to come up with an ISA. And so they released the frozen user spec in 2014. So that was version 2 of the ISA. And so they taped out several RISC-V chips since then, sort of along the way. So they've done 10 or so test chip tape outs. So I'll give you a little bit of background on sort of a RISC. Let me put this away. So RISC stands for Reduced Instruction Set Computer. So in general, you're looking at sort of smaller, less complex instruction sets. Most of the chips that are out now, aside from x86, are RISC chips, and so these are load store architectures. So if you want to operate on memory, you have to load them into registers, operate on them there, and store them out. And they tend to be easy to implement and efficient. So some of the seminal RISC processors were the Berkeley RISC-1 and RISC-2. So David Patterson at Berkeley designed these, and they heavily influenced the SPARC architecture. So if you're familiar with register, okay, we're back. So if you're familiar with SPARC, register windows actually came from the RISC-1 and RISC-2. And then around the same time, this was in the early 80s, Stanford, John Hennessy was working on RISC at a It's better. Okay, we're back. All right. Cool. So yeah, about the same time, Hennessy was working on at Stanford on the Stanford RISC processor, and that became a MIPS. And so when MIPS got sold, Hennessy made a lot of money, so he's rich now, and he's also the president of Stanford now. Another RISC, and he made even more money actually as the president of Stanford because he was able to invest in a number of these Stanford startups. So he's really rich. So, but he still puts out architecture textbooks. So I'm a fan. So an ARM is another well-known RISC chip that stands for Advanced RISC Machine. It used to be Acorn RISC Machine. And speaking of ARM, I don't know if you had a chance to see Andy Turner's talk on ARM v8. It was really good, and you should check out the video if you haven't. So ARM v8 and RISC-V, you'll see that there are a fair number of similarities. And the reason why that is because they have sort of a common history. So I found this presentation from Nigel Stevens. He's the lead ISA architect at ARM, and he used to be a former MIPS designer. And so one of the quotes from that talk is that ARM v8 has lost some idiosyncratic ARM features, remains as more a conventional RISC ISA. So similar to MIPS, Alpha, PowerPC, HPPA, which all follow the same line of descent from Stanford RISC or Berkeley RISC because they were fairly similar. So RISC-V and ARM v8 share kind of a common lineage. And so if you look at MIPS, if you look at ARM v8, if you look at RISC-V, there are a lot of similarities. Man, so this is sort of going back a little bit, looking at like Alpha and HPPA. So these are architectures that are sort of long dead, but Alpha was a pretty cool architecture back in the day. It came back. I can scream, I guess. Yeah, I guess. Okay. It won't help the live stream. We'll try it and then we can switch if it doesn't work out. So there are a number of other open ISAs. OpenRISC is one that you may have heard of. It's MIPS-like. There's the Open Processor Foundation. This is kind of interesting. So as the Super H patents have been expiring, they've been re-implementing them as what they call J cores. So that's kind of interesting. So they have microcontroller class processors. I don't think they have out-of-order cores yet, but they will. Spark v8 was an open ISA. Apparently it was an IEEE standard. Spark v9 isn't, it's proprietary, which is when Spark became a 64-bit. More familiar to this community may be Berry and Cherry. So Berry is about, I think it's like a mid-90s MIPS 3. And then Cherry is the capability-enhanced Berry processor. And so you may have seen some of the talks that Brooks Davis and David Chisnell and Robert Watson have given on Berry and Cherry. It's a pretty interesting platform. So these are all interesting ISAs. I think the community, I think RISC-V has more of a potential to kind of build a larger community. So although these are very interesting processors, I think there's been a fair amount of cross-pollination between these projects. So I know that Robert Watson and David Chisnell have given a lot, who worked on Berry and Cherry, gave a lot of feedback to the RISC-V team on their various specifications. So there are a number of RISC-V projects at a number of different institutions. Berkeley has a large number of processors. These are all open source, and they're written in Chisel, which is their hardware description language. So Rocket is kind of they all have train themes for some reason. I guess someone really likes trains. So Rocket was a famous train, apparently. So Rocket's a 5-stage pipeline, single issue, so it's kind of a standard. It's supposed to be kind of like a Cortex A5 you can sort of compare it to. Boom hasn't been released yet, but will be released at the end of this year, and that's going to be their out-of-order core. SOTA is their collection of educational cores, so this is what they teach in their university courses. So they have several cores from 1-stage to 5-stage pipelines. Zscale is supposed to be their microcontroller, so this is kind of like your Cortex-M like processor. And so these are all open source implementations from Berkeley. Zscale was released fairly recently. Also, you have the Low Risk project based out of the University of Cambridge. And it's from the same people that created the Raspberry Pi. So they founded this new open hardware project. And so they've called it Raspberry Pi for grown-ups. That's kind of like their tagline. So whereas Raspberry Pi for there are a lot of grown-ups who use Raspberry Pi as well, but the low-risk thing is kind of an interesting platform. They have a couple kind of cool researchy features. So they made it a tagged architecture, which adds some interesting sort of security features. And they have kind of an interesting I/O architecture to do offload called Minion cores. And if you're interested in this stuff, they have a couple white papers that are out there, and they're actively developing it. And they're an open source project. They were part of the Google Summer of Code this summer. And so their goal is actually to build like a completely open hardware board. And so they're trying to ship boards in a 2016 or 2017 timeframe, so actual silicon. So that's pretty cool. So IIT Madras is also doing some RISC-V work. Apparently, India has decided that RISC-V is going to be the standard ISA for the country. So it's kind of interesting. So they put a fair amount of money that they've given to IIT. And they're building 6 different open source cores. So they're actually building microcontrollers, and they're actually trying to build supercomputers. And so they're building, and it's going to be open source. And they're writing that in the BlueSpec hardware description language. Speaking of BlueSpec, they're an EDA company based in Boston. And so they're also developing proprietary RISC-V cores and IP blocks. They may open source some of their stuff at some point, but it's not clear. Then there's a number of various hobbyist implementations of RISC-V. So one that's somewhat popular is Yarvi, yet another RISC-V implementation. And you can find a whole bunch on GitHub. And you could make your own if you wanted, because the RISC-V ISA is fairly simple. There's a fair amount of RISC-V software that exists. This is one thing that I think Berkeley did well compared to some of the other open hardware projects back in the day. So they have tool chains, there's GCC and binutils. There's a Clang and LVM port that's kind of in progress. It's not fully functional yet, but it's getting there. They have a number of kernels. So they have this really simple kernel that's basically just for testing called a proxy kernel. So it runs like a single application and redirects some system calls. So they have a Linux kernel port, and they also have, this was a Google Summer of Code project. Someone ported SEL4, which is this formally verified microkernel from NICTA, the University of New South Wales, and that was ported to RISC-V this summer as part of Google Summer of Code under the low-risk project. In addition, Berkeley's done some Linux distributions, so there's Gentoo and there's Open Embedded Pokey. So none of this stuff has actually been merged upstream. It's all in kind of like under the RISC-V GitHub organization. We've been trying to help them kind of, and other people in the RISC-V community have been trying to help and kind of encourage Berkeley to kind of get this stuff upstream to make it easier to maintain. So that's going to be sort of an ongoing process. But if you want to contribute to any of these projects, they're all on the GitHub RISC-V organization. The Berkeley guys are really good about taking patches. I've submitted patches for various parts of the stack, and they're very good about kind of integrating pull requests and accepting feedback. So please get involved. So as I said, you might be thinking, oh yeah, RISC-V sounds cool. I really want to get some hardware. Where can I get the silicon? You can't yet. So if you want to play around with RISC-V, you either have to do an emulator or an FPGA. So the kind of golden standard ISA instruction set simulator is called Spike or RISC-V ISASIM, and so that's what we've actually been using for development. They have a JavaScript emulator, which is kind of cool. You can boot Linux in a JavaScript emulator. There's also QEMU RISC-V target. Unfortunately, it's out of date, so Berkeley's been kind of they've had different versions of their privilege specification, and so this version of QEMU supports an older version of that specification. And so the Berkeley folks are working on getting it up to date, but it's taking longer than they expected. So in the next few months, there should be a QEMU backend that you can use, and will make it a little bit more convenient to do kind of OS bring up and things like that. So if you're into FPGAs, you can grab the Zybo board or the Z board, and these are kind of cool platforms anyways. They have an ARM Cortex-A9 on there along with some FPGA fabric, so it's kind of cool if you want to do development, if you're doing any hardware development. So the Zybo, I think, is about a couple $100. The Z board is around $400 USD. I have the Z board. It's a little bit bigger. It's pretty nice. It also runs on other Xilinx FPGAs as well. And then hopefully in 2016, 2017, you'll be able to get actual silicon hobbyist boards from low risk. The Berkeley guys do have a bunch of test chips that they've been fabricating, as I mentioned earlier. So they're one of the few people that actually have RISC-V hardware out there, or RISC-V silicon at least. So this is probably one of the most important slides in the presentation. So if you want to read more about what RISC-V looks like, you read the specifications. So the nice thing about these specifications is they're fairly short. So the user level ISA specification, which is frozen, came out in May 2014. It's about 100 pages, fairly readable. The nice thing about it is that compared to other specifications, they actually have commentary that talks about, hey, why do we do this? Or what are some of the alternatives? So it's actually kind of an interesting read if you're into architecture. They have drafts of their privileged ISA specification, so kernel hackers among you should read this, and Berkeley wants to have feedback, so it would be really good if more BSD kernel hackers looked at it and gave feedback to the RISC-V people. So that came out in May of 2015. They also have a compressed ISA specification, which is also a draft, and this it's basically, they have sort of compressed instructions that are supposed to improve your like code density. So it's supposed to operate, it's similar to what ARM has done with Thumb. So to quickly overview the ISA, so as I mentioned, the kind of methodology they have is they have a small base integer ISA and they have various standard and non-standard extensions that you can add. But to be a RISC-V core, all you have to do is implement the base integer ISA. And so that's about less than 50 hardware instructions, so it's fairly small. They have 32-bit, they have a 32-bit architecture, a 64-bit architecture, and they have a 128-bit architecture specification as well, because why not? David Patterson was saying that they have found some use in various data center applications, so there are people who are interested in 128-bit now. Exciting times. So in addition to this base integer ISA, there are a number of standard extensions that you can add, and most processors will probably implement them except for kind of your small microcontrollers. For instance, so there's the M standard extension, which is the integer multiply divide. A is your atomic memory operations, F is floating point, D is double floating point. And those four extensions together are so common that they kind of lump them together as the general purpose ISA. So most your standard operating systems are going to run on G processors. So like Linux and BSD will run on RISC-V 64, 32G. They also have a quad processor floating point extension as well. They're going to have a number of extensions that they're going to be releasing over time. They have plans for security extensions, transactional memory. They don't have hypervisor spec yet. That's something they'll be working on. So there's a fair amount of other extensions that probably people will be coming up with. And then various researchers and other groups will come up with their extensions as well. Some of them will be non-standard, so they won't only, they'll be sort of special sauce for that particular company, but there will also be sort of other standard extensions as well. So these are the registers that are available on RISC-V 64-bit. If you saw Andy Turner's talk, it's fairly similar. So you've got 32 64-bit general purpose registers. Depending on how you count, it's 31 or 32 because one of the registers is a 0 register that always has a 0, so that's X0. So by convention, X1, X2, and X14 have special uses, but they're actual general purpose registers. So X1 is your return address register, or RA, so that's like your link register on ARM. X2 is your frame pointer, and X14 is your stack pointer. In addition, there's a program counter. So RISC-V assembly looks a lot like MIPS. So there are a lot of sort of assembly macros and aliases that you'll find in the assembler. So you'll put some sort of assembly instruction in, and it turns out the assembler will actually turn that into another like real hardware instruction. Unfortunately, there's no actual assembly guide yet, so you kind of have to just kind of like look at existing code or check out some MIPS books because a lot of the instruction set is fairly similar. and then you can read other source code. So a few good books. You probably can't read this picture, but the two Hennessy and Patterson books are good if you're going to be doing any architecture. They go over MIPS. The Computer Organization Design book and the Computer Architecture Quantitative Approach book are both good. And then the CMIPS Run book is also good because it talks about both the user spec, but also talks about the Linux port on MIPS as well. So not all of this will apply to RISC-V, but a fair amount of the user stuff does. So I'm going to quickly go over the RISC-V assembly syntax. So this is a program that just adds the numbers, adds 1 and 2 together. So basically you load 1 into register X1, you load 2 into register X2, and you've got a 3 operand add. So X1 and X2 get placed in X3. So it's kind of standard. The load immediate is actually it's a pseudo instruction. So this actually gets turned into a 3 operand instruction with the 0 register under the hood. So this stuff is useful just so when you're bringing up kernel stuff, it's good to at least be able to look at the disassembly, and especially when you're doing a low-level bring-up, you're looking at a fair amount of assembly code. So as I said, it's a load store architecture, so this is how you load things. So this will load what X1 points to an X0, and this is how you store what's in X0 out to X1. And then you've got your standard control flow instructions, your branches, calls. RISC-V doesn't have a condition code register, so that's a little bit different than, say, x86 and ARM. So the call function does what you'd expect, calls a function. That's also a pseudo instruction. It'll typically call a jump and link instruction, which will save off the return address to your return address register, or on ARM, it's called the link register. And then return is the same as just jumping to the return address register. So this is basically a quick primer on RISC-V assembly if you have to kind of get down to that level. If you saw Andy's talk, this looks pretty similar to ARM v8. So level 0 is where all the user mode application code runs. Level 1 is where the supervisor mode, your BSD code runs. Level 2 is where all the hypervisor magic happens, so Zen, Beehive. Level 3 is where machine mode, that's where your firmware runs. Because RISC-V is supposed to be kind of configurable, machine is the only required level. So you can have a microcontroller that only supports machine mode. If you're doing any low-level hacking, you'll be messing around with the control and status registers. So especially if you're doing kernel stuff, you'll be twiddling bits using the CSRs. There are different registers for kernel, hypervisor, and firmware modes. And these are used to configure your system properties, your memory management unit, interrupts, etc. So one important register that I'll just highlight quickly is the status register. There's a machine level status register, and there's also supervisor level status register, M status and S status respectively. And so this holds like your current privilege mode, your MMU mode. This is how you enable interrupts. It also holds your pass mode and interrupt status for when you hit an exception. The S status is actually a restricted view that's available in S mode. Not all of the bits are available, which becomes important a little bit later. So this is how you write it. There's a CSR-R, that's the read instruction, and CSR-W is the write instruction. So you can do the same thing for M status and S status. So the syntax doesn't matter. You can look it up, or it's in the presentation. They have a number of standard exception types. So if you want to do a system call, you use the eCall instruction. It used to be scall, but they wanted to have the same instruction for each of the levels. So basically an eCall is how you get to a more privileged level. So from user mode, you can go into supervisor mode. From supervisor mode, you can go to hypervisor mode, and all the way down. Then there's memory faults, illegal instructions, breakpoints. There's also interrupts, so there's timer interrupt, software interrupt. RISC-V doesn't have like an interrupt controller defined yet, so that's something they have to define. So eventually you'll have other devices and things like that. So they haven't really defined the sort of like SoC architecture yet. They're kind of like coming up with that. If you're doing exception stuff, there's a few other registers you want to know about. The SEPC is a supervisor exception program counter. So this is a virtual address of the instruction that kind of encountered the exception, so you know what caused the exception. SCAUSE is the supervisor trap cause. This is what caused the exception. And SBAD adder is the supervisor bad address. So this is your faulting address for memory faults. And RISC-V has a number of different memory modes. As I said, RISC-V is supposed to run from microcontrollers all the way to supercomputers. So in some cases, you may want really simple memory management or no virtual memory at all. So this is how you determine the virtual memory translation protection scheme. You set the virtualization management field in the M status register. So for microcontrollers, you can have MBARE, which is no translation or no protection. So this is for CPUs that only support M mode. So this is the VM mode that you have on reset. So you start off with no translation, no protection. To actually have some protection, you can have MBB and MBB ID, so that's base and bounds protection. So this is sort of like segmentation on x86. So if you have user mode, you can support this. And then you have your standard page-based schemes for CPUs that support supervisor mode. And this looks a lot like ARM v8 or AMD 64. You've got a hardware-managed TLB, so the MMU does the page table walk on a TLB miss. So this is different from MIPS. You have up to 4 levels of page tables. You have various page sizes from 4K all the way up to 512 gigabytes. And then you set up the page table by writing to the supervisor page table base register. And this is the instruction to do that. You just use CSRW to write to the SPTBR. And so there's a number of different schemes that it supports. There's SV32, which is 32-bit virtual addressing for the 32-bit processor. The page tables are kind of like x86 10.10.12. Then there's SV39 and SV48 for 39-bit virtual addressing and 48-bit virtual addressing, respectively, on RISC-V 64. So I'll talk a little bit about the FreeBSD RISC-V port because that's what we're trying to bring up. So we're targeting the 64-bit RISC-V processor and an SV39, which is also what the ARM v8 port that Andy talked about supports. And so we're largely basing it on the ARM v8 porting process and sort of bringing it up and using as much code from ARM v8 as we can. And Ruslan has been doing a lot of the most of the heavy lifting. He's the one who's actually kind of brought up the kernel and done all of that stuff. So Ed Mast and myself have been helping out a bit, but Ruslan's really the one who's kind of made all of this stuff happen. And so the basic kernel bootstrapping is done. It boots up to the mount root. And unfortunately, we're using GCC as a tool chain since Clang's not ready. So there is a NetBSD RISC-V port in progress that Matt Thomas is working on, I believe. And there's early kernel support, but I don't think the VM bits are there. If there are any NetBSD people here, you can correct me. But I think the port's ongoing, so it'd be cool if that gets up and going as well. And then as far as I know, there's no OpenBSD RISC-V port, but I think that would be really cool. And I think OpenBSD, since with their focus on security, they might be particularly interested in open hardware. So we have some of the code up on GitHub, and some of the code's going to change, but I'm going to quickly kind of tour the code that exists. So most of the code, we're looking at architecture-specific stuff. So that falls under sys RISC-V, includes sys RISC-V, RISC-V, and then these are the various configurations files you can figure out to what gets built, so you can figure out what gets built. So I'll do a quick aside on booting, just because it's good to know. So in the typical boot process, what you have is you have firmware that runs, so something like a BIOS or UEFI or U-boot or an SoC ROM. Then your bootloader runs, and that loads your kernel. And so the firmware and bootloader share a couple of responsibilities. They'll do low-level hardware initialization, so DRAM, serial, they'll pass some boot parameters to the kernel, and then the main job is to load the kernel. And so your typical options are something like an SoC ROM and U-boot and then loader rate. So this is the case on ARM v7, for instance, for the BeagleBone Black. For ARM v8, there's something like, or on x86 as well, you have UEFI. Tiano Core is a popular implementation of UEFI. And then you have your loader rate bootloader. And you can either get your device configuration either from flattened device tree or ACPI. So for server class machines, a lot of time it comes from ACPI. So on RISC-V, what you have is they have something called the Berkeley bootloader, and so it's the firmware and the bootloader. And when you boot it up, you get this kind of cool ASCII art logo. I like ASCII art, so it's kind of exciting. And at the end, you get the kind of like tagline for RISC-V, instruction sets want to be free. So it's kind of cool. On FreeBSD RISC-V, we don't actually use BBL currently, so you don't get the cool ASCII art. We're actually re-implementing some of the BBL functionality for sort of ease of development, because you can just sort of like boot up the kernel without actually having to build this. In the long term, we'll probably port loader 8, so you have like a real bootloader. And once RISC-V sort of comes up with a boot spec, once they decide what are they going to do, are they going to use something like U-boot, are they going to use UEFI, then we'll kind of like follow whatever the specification for the architecture is. Like for instance, ARMv8 has a boot specification that FreeBSD follows. We are using device tree on RISC-V. It's used by Linux and FreeBSD on several architectures, MIPS, ARM, ARMv8. And so device tree is a data structure that describes hardware configuration. So this is how you configure. It captures the configuration for the timer here. And so you can find this in the spike.dts file. And so this gets converted into a binary format that the kernel can parse. So here's a boot log from FreeBSD RISC-V booting. So I'll quickly go over it. So Spike is the instruction set simulator. That's how you run things. Then a bunch of stuff happens. Init RISC-V runs. You get the copyright notice. You're kind of into machine-independent code. You'll enable interrupts. You run start init. And right before VFS mount root, that's kind of where things go bad because that's about as far as we've gotten. So I'll do a quick demo. And Ruslan actually did all this work, so he did a great job there. So, and there's a lot of extra sort of debug output there. So you run Spike, and then you build and you run the kernel image. And so you're going to see a whole bunch of debug output that's going to scroll by. A whole bunch of PMAP stuff and all kinds of stuff. I sort of trimmed it down so you could see kind of the key bits. So it'll keep running, and then it will die when it tries to mount root. So lots of debug output. So this is as far as you get into the kernel boot. And then once you're in Spike, you can kind of step through instructions, which is kind of cool. And then there's a help thing. If you want to print out registers, you can do that. So it's kind of a standard instruction set simulator. I actually wanted to show this earlier. We'll do it now. I'll do it after. How much time do I have? Okay. So quickly, I'll go over the kind of kernel initialization process. So there's kind of like what you saw there, a lot of what had to happen is the early kernel initialization. So a lot of saving off the boot parameters, you set up an initial page table and enable the MMU. You set up an exception vector table and handlers. And then after that, you'll do some device initialization like serial and timers for the clock tick. Then you get into the machine-independent initialization. That's when you actually see FreeBSD, the copyright logo, getting printed out. You'll initialize more of the kernel subsystems, do some more device initialization. Then you'll enable interrupts, and then you'll switch to user mode and run init after mounting the rootfs. So we're almost to the point where we can run init once Ruslan's doing some more of the userland bring up, and so then we'll be able to do that. So I'll show you a little bit of code that exists. Some of this is going to change, but these are sort of like the first instructions that happen. So that's an locor.s. And so this replicates some of the functionality the Berkeley bootloader would do for us. So one of the first things you have to do is set up an initial page table, and you have to switch to supervisor mode and enable the MMU. So that's one of the first things you do. And so basically you write the SPTBR register that I mentioned earlier. And to go from machine mode to supervisor mode, typically, to go to a more privileged mode, you do an eCall. To go to a less privileged mode, you do an ERET, which is an environment return. So that's how it does it. It sets the instruction you want to jump to there. So the details don't really matter, but you can look this up. So those are roughly the first instructions. So then start will sort of continue execution. It sets up the environment for C code. You don't want to have to write all of your startup code in assembly, so What it does is it'll set up your BSS and set up the stack and all that stuff. And then it'll call the first C function, which is init RISC-V. And so that'll continue the RISC-V specific initialization. And so if you look at mockdep.c, you can see that stuff. It stands for machine-dependent code. And so this will map devices, initialize the console, it'll set up the real page table and switch to it. Then you kind of get into your machine-independent code. So that's MI startup. That's the entry point for machine-independent code. Then you get your copyright notice. And then you get into all of the rest of the kernel boot up, and then you kind of, if you can mount the rootfs, you get into init. And so once the kernel is booted up, which we're not quite there yet, but a lot of what will be happening is handling exceptions. So I'll kind of skip over that briefly because there's a fair amount of details. So I'll mention there's an MTVEC and STVEC register that you'll need to know about, and then you have to set up exception vector table, the code's in locor.s, and then you have to write a handler. And so it saves some state, it calls dotrap, and then restores the state, calls eret. So I'm going to skip through these stuff in the interest of time. But if you want to figure out how this stuff works, just look at this code, and trap.c has more of the details on how it kind of looks at the cause register to figure out what's going on, and then jumps to the appropriate handler, and then calls load registers in eret. So if you actually want to develop FreeBSD RISC-V, you can run make build kernel target equals RISC-V and then a whole bunch of other stuff. And the whole bunch of other stuff is on the FreeBSD RISC-V wiki page, and I'll have a link to that a little bit later. And so there are a number of target platforms that you can run this stuff on. So there's the Spike simulator. That's actually what we've been using. Eventually, you'll be able to use QEMU, and then if you have access to these FPGA boards, they're pretty nice. And then you could also try running it on, eventually we should be able to run it on the JavaScript simulator that Berkeley has. So sort of the short-term and somewhat longer-term to-dos for FreeBSD RISC-V is that the GCC bin utils toolchain needs a fair amount of work. It was kind of a quick hack to put it together. It would be good to package up the RISC-V simulators and toolchain to make it easier for other people to get up and running, so you don't have to like build Spike and by yourselves. And then more of the userland bring up, and Ruslan's starting to look at this. And then longer term, it would be great to have some more work on the Clang LVM RISC-V backend. So if you're a Clang hacker, it would be great. Please start working on RISC-V. You have a question?
What's the Spike license?
BSD. Everything's BSD, actually. Yeah. Everything Berkeley's put out. So reading this, all the specifications are worth reading. There was, as I mentioned, there were 2 RISC-V workshops. All the slides and videos are online. They have a lot of quick start guides. If you want to do hardware development, they actually they kind of walk you through how to like synthesize the core and do all of that stuff onto an FPGA. So that's useful. There's a fair amount of, in addition to BSD source code, looking at the source code for the simulator Spike is useful. You can look at the Linux port as well as the firmware, the Berkeley bootloader code. There are a number of upcoming RISC-V events. So if you're going to be in Geneva next week, October 9th through 11th, there's the Open RISC Conference. It's also functioning as the RISC-V Low Risk European Conference as well. So there's a number of interesting talks. I was hoping to make it, but unfortunately I won't be able to make it. Then there's also a 3rd RISC-V workshop in January in California. And then there's another RISC-V workshop in Boston in the summer, which is where I've been living for the last couple of years. So you should come to both of those and say hi. And it's a good thing they're having it in Boston in the summer, because Boston in the winter is not ideal. So yeah, good call there. And if you want more information on our FreeBSD RISC-V, the wiki page will show you how to build the stuff. There's an IRC channel on FNet, FreeBSD RISC-V. There's a mailing list, FreeBSD RISC-V at freebsd.org, and then all the codes on FreeBSD RISC-V GitHub organization. So in summary, RISC-V is a new open instruction set. That's the one thing you have to remember. And there are lots of exciting RISC-V projects that are out there, interesting research projects and implementations. There are actually people building RISC-V products. Someone was building a camera using RISC-V as their ISA, which was kind of cool. And then finally, BSD RISC-V is happening, and it would be great if other people could contribute or work on other BSD ports as well. And if you want to help the larger RISC-V community, please, if you're an architect or a kernel hacker, comment on the various RISC-V specs, contribute to the source code, all their sources on GitHub. They're really good about taking pull requests. You can make some RISC-V hardware yourself. You can port RISC-V to your BSD of choice or whatever other operating system you're interested in playing around with, like FreeRTOS or various microkernels or things like that. And then please, 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 someone contribute to the Clang LVM RISC-V backend. That would be awesome. And you could also port various applications of RISC-V. I know someone did an OCaml port of a RISC-V, which was kind of cool. And so, in conclusion, please start hacking RISC-V. You can grab some virtual or reconfigurable hardware and start hacking either RISC-V software or hardware. And so, with that, happy to take questions. If you have, and also feel free to email me. Sure. So they have sort of instruction. Oh, sure. So he wants to add an integer instruction and a floating point rounding mode. Okay. So I don't know about the floating point rounding mode because I haven't really looked at the floating point instruction, but it should be doable. For the adding an integer instruction, that's fairly easy because they have templates of how to add that stuff, and then they also have encodings available. Oh, you want to get into the spec. So basically, you'll email the ISADEV instruction. There's an ISADEV list, and so you should post your proposal there. And so various folks like Andrew Waterman, Jonsip Lee, Krista Sanovich, David Patterson will respond. Okay, so I see. You actually want a standard extension. Okay. So yeah, that's good. So you want to modify the user spec then? Okay. I think that might be a little bit harder to do, but what they have talked about is adding sort of B extensions, so popular instructions that most people might want to implement, but probably won't go into the I base instruction set. So. Okay. Yeah. So I think they'd add that. Yeah. So I think they'd add that as a standard extension, but not as part of the the base and integer instruction set. So yeah, I would email ISADEV and then someone will respond to you. There's been a fair amount of traffic recently, so yeah, that would be a good way to do it. You had a question? Yeah, so there's a test suite that they have that runs a bunch of assembly tests and things like that. SRI has been doing some interesting work on actually building a formalized model of the ISA, and I know that the Cherry team has been doing some fairly interesting stuff in terms of ISA formal verification as well. So I think there's going to be some interesting sort of cross-pollination there. So, but there is a large test suite that you can get on the GitHub site called our RISC-V tests and RISC-V test env. So it's a lot of sort of low-level instruction sets, low-level instruction tests and things like that. But yeah. Sure.
I also want a RISC-V laptop. How do I get that?
So one of the guys, so Bunny Huang, I don't know if you're familiar. Okay. You have his Novena thing. Okay, so he's on the board for low risk. And so maybe when low risk kind of releases their board, and then once they have their sort of developer board out there, maybe in the future they'll kind of have a laptop as well. I mean, the other thing you could do is build your own laptop, I guess, if you wanted to. You could team up with Bunny.
I've actually been thinking of trying to use the FPGA on that.
Oh, okay. Yeah.
I haven't done anything about it yet.
Yeah, that's a good idea. Any other questions? I meant to show this earlier, just because it's kind of cool. Where was it? Yeah, here it is. So I meant to show this earlier. So this is Linux actually, but it's still kind of cool. So this is the JavaScript emulator. It's called Angel, and it runs on Chrome, and so you can boot Linux on it. So, and eventually we should be able to boot BSD on there. And so it runs about 15 million instructions per second. And so I can run uname, and it's running RISC-V. So it's kind of cool. Hopefully we can get a FreeBSD running on there. So it's kind of a neat little trick. It apparently runs a lot. They warn you not to run it on Firefox. I guess the Chrome JavaScript engine is a lot faster than the Firefox one. This, I have no idea, probably not. Maybe? I don't know. You can try it. Seems like it should. It's got the same JavaScript engine, so.
It's current base run from nodes.
Yeah, so they both have V8. Other questions? Great, thanks a lot, appreciate it.
Node, you might be able to get 35, 40 minutes. Which is like,
Sure, it was a little rocky.